Every technician has a breaking point, every single one. And it's not the broken compressors or the frozen coils, it's the calls. Here are 71 of the most spectacularly wrong things customers have ever believed about their HVAC systems. 1. The moment your air conditioning stops cooling, you've already diagnosed it yourself, and the diagnosis is always the same. It's out of Freon, just top it off, write you a check, everybody goes home happy. Here's what nobody told you, and what the technician standing in your driveway is too polite to lead with. Refrigerant is not a fuel. It does not get consumed. It does not burn off. It does not evaporate into the atmosphere through sheer hard work and dedication. It operates in a completely sealed loop, and the exact same charge that was installed at the factory is supposed to be in that system for the entire lifespan of the equipment. If your system is low on refrigerant, there is a leak, full stop, and adding more refrigerant without finding and repairing that leak is the mechanical equivalent of pouring water into a bucket with a hole in the bottom. Feeling very accomplished, and then wondering why the bucket is empty again next Tuesday. The most common reasons your AC stops cooling have nothing to do with refrigerant at all. A clogged air filter restricting airflow accounts for roughly 25 to 40% of all residential service calls, a failed capacitor, a frozen evaporator coil, a faulty compressor. A dirty $5 filter is the culprit so often it borders on a running joke among technicians. And here's the legal reality nobody mentions at the hardware store. Your technician cannot legally just add some refrigerant. The EPA requires a Section 608 certification to purchase and handle refrigerants, and adding charge without a leak diagnosis and repair first is a federal violation, not a preference. The bucket has a hole. Find the hole. 2. Your thermostat is lying to you. That's the conclusion you've reached, standing in a room that feels like the inside of a pizza oven while the display reads a perfectly reasonable 72 degrees. The thermostat is defective, the thermostat is broken, replace the thermostat immediately. Except, here's the part that's going to be mildly inconvenient for your theory. Modern digital thermostats are extraordinarily accurate, typically within half a degree Fahrenheit of actual ambient temperature. They are not the weak link in the system. They are, in fact, one of the most reliable components in the entire setup. The real problem is almost always where the thermostat is located and what's sitting next to it. A thermostat mounted on a wall that receives direct afternoon sunlight will read artificially high because it is accurately measuring the surface temperature of a sun-baked wall. A thermostat positioned above a lamp, near an oven, or adjacent to any heat-generating appliance is measuring exactly what's around it, and what's around it is warm. This is not a malfunction, this is physics doing its job correctly. There's also the uncomfortable reality of human thermal perception, which is nowhere near as objective as you think it is. Your actual comfort is influenced by humidity levels, radiant heat from walls and ceilings, air movement, and your own metabolic rate. Two people standing in the same 72-degree room can genuinely perceive the temperature as being 4 to 8 degrees different from each other depending on activity level and humidity. ASHRAE defines the human comfort zone as 68 to 76 degrees at 30 to 60% relative humidity, and perceived temperature shifts dramatically outside those humidity parameters. A thermostat replaced unnecessarily runs between $150 and $500 in parts and labor. The actual fix is often repositioning the unit or adding a small circulation fan, which costs nothing. The messenger is not the problem. 3. You've discovered a life hack. You've closed every single vent in the guest room, the storage room, the basement, and the hallway nobody uses, and you're redirecting all that beautiful conditioned air to the living room where it actually matters. The bill should go down. The comfort should go up. You'd like to know why the bill went up and there's ice on your indoor coil. Here's what happens when you close supply vents in a forced air system and pay attention, because this is the opposite of everything your instincts told you. Your HVAC system was engineered to move a specific volume of air, measured in cubic feet per minute, through the entire duct network simultaneously. Every branch, every register, every return grill was calculated as part of a balanced system. When you close vents, you do not redirect airflow. You increase the static pressure throughout the entire duct system, and pressurized air finds the path of least resistance, which is almost never your living room. It's the duct leaks. The average American home loses 20 to 30% of its conditioned air into unconditioned wall cavities, attics, and crawl spaces through duct leakage. When you increase system pressure by closing vents, you're turbocharging that leak rate. Meanwhile, the elevated static pressure forces your blower motor to work harder, consuming more electricity and shortening the motor's lifespan, which is the opposite of your stated goal. The reduced airflow across the evaporator coil drops the coil temperature below 32 degrees Fahrenheit, and now you have an ice block where your cooling coil used to be, which eventually shuts the whole system down. Energy Star research confirms that closing vents in 1 or 2 rooms produces zero reduction in energy consumption. It simply moves where the energy is wasted. Zoned systems with engineered dampers exist specifically to do what you were attempting. This was not that. 4. You've made your decision. The AC isn't keeping up, and the solution is obvious. You need a bigger unit, more tonnage, maximum power. You want the largest system the technician has on the truck installed by Thursday, and you'd appreciate it if the lengthy explanation could be abbreviated because you're busy. Here's the abbreviated explanation. An oversized air conditioning unit is one of the most damaging things you can install in a residential home, and the damage is quiet enough that most people never connect the dots. When a system is too large for the space it serves, it cools the air so rapidly that it satisfies the thermostat set point before it has time to adequately remove humidity from the indoor air. Humidity removal requires the evaporator coil to stay cold long enough for moisture to condense and drain, a process that takes at least 10 to 15 minutes of sustained runtime. An oversized unit runs for 3 minutes, shuts off, and your house is cold and clammy and growing mold in the corners. This is called short cycling, and it is also the most mechanically destructive operating pattern for a compressor. Every startup draws the highest electrical load in the entire operating cycle, and a system that starts and stops every 8 to 10 minutes is accumulating compressor wear at a rate that turns a 15 to 20 year equipment lifespan into 8 to 12 years. The Air Conditioning Contractors of America estimates that a significant percentage of residential systems are already oversized, not because customers demanded it, but because contractors stacked safety margin on top of safety margin until the number looked impressive. The correct size is determined by a manual J-load calculation, which accounts for your actual square footage, ceiling height, insulation values, window area, and local climate. Bigger is not better. Right-sized is better. 5. You've heard that running the system fan in the ON position keeps the air circulating constantly, filters the air more thoroughly, and somehow reduces the workload on the equipment. Sounds logical. Costs you money every single month and quietly raises your indoor humidity to levels that make your home friendlier to mold than to you. Here's what actually happens when the fan runs continuously. In auto mode, the fan operates only when the system is actively heating or cooling. In on mode, it runs 24 hours a day regardless of whether any conditioning is occurring. The problem arrives the moment a cooling cycle ends. When the compressor shuts off, the cold evaporator coil begins to warm back up, and any condensation that formed on the coil surface starts to re-evaporate. With the fan still running, that re-evaporated moisture gets pushed directly back into your living space, raising indoor relative humidity. In a humid climate, this effect alone can increase indoor relative humidity by 5 to 10 percentage points, which is enough to push conditions past the 60% threshold where mold begins to colonize surfaces. Your air handler fan motor running continuously consumes somewhere between 300 and 600 watts. Running it 24 hours a day, 7 days a week, adds $30 to $50 per month to your electricity bill in warmer climates, which is in many cases more than the cooling system itself during shoulder season months. Continuous fan operation also loads the filter faster, which restricts airflow sooner and reduces system efficiency before you've gotten to the end of the filter's rated service interval. The one legitimate application for continuous fan operation is in homes with specific whole home ventilation systems where the fan serves a separate mechanical purpose That is not your situation. Auto mode exists for a reason. 6. It is January, it is cold, and your heat pump is blowing air that feels cool against your hand. You've called the company, explained that the system is blowing cold air in heat mode, and you've already decided it needs to be replaced before the weekend because your neighbor, who is not an HVAC technician, confirmed over the fence this morning that yes, this definitely sounds broken. Your heat pump is almost certainly operating exactly as it was designed to operate. A gas furnace produces supply air at 120 to 140 degrees Fahrenheit. A heat pump in standard heating mode produces supply air at 90 to 100 degrees Fahrenheit. That air is warm enough to heat your home. It is not warm enough to feel hot against your palm, which is what you've been unconsciously expecting based on a lifetime of gas heat experience. The technology works differently, and different is not broken. Heat pumps extract thermal energy from outdoor air using refrigerant and transfer it indoors, even when outdoor temperatures are in the 30s and 40s. This seems counterintuitive. It is thermodynamically sound. When outdoor temperatures drop below approximately 35 degrees Fahrenheit, most standard heat pumps lose efficiency and supplemental electric resistance strips engage as backup. Customers frequently experience this transition and interpret it as a system failure. The defrost cycle also causes the system to briefly blow slightly cooler air for 5 to 15 minutes while the outdoor coil sheds ice accumulation. This is a designed operating mode with a specific purpose. It is not a malfunction. Heat pump efficiency is measured in COP, coefficient of performance, and a standard heat pump delivers 2 to 4 units of heat energy per unit of electricity consumed. Cold climate heat pumps maintain full heating capacity down to negative 13 degrees Fahrenheit. The system is working. The expectation is what needs updating. 7. You leave for work every morning and turn the AC completely off. The house climbs to 85 degrees by afternoon. You come home at 5, crank it back on, and by 9 in the evening, the house is comfortable again. You've been doing this for years, the bill seems reasonable, and you're calling today because someone at the office told you, this approach is actually worse for the system, and you'd like a second opinion. The person at the office is correct. When you allow a home to reach 85 degrees during the day, every object inside that home absorbs heat energy. The walls, the flooring, the furniture, the framing, the drywall, all of it. This is thermal mass, and it stores an enormous amount of heat. When you turn the AC back on at 5 in the afternoon, the system has to remove not just the temperature from the air, but all of the heat energy stored in every single object in the building before the indoor temperature will stabilize. This is a dramatically more energy-intensive event than simply maintaining a moderate setback temperature throughout the day. The Department of Energy recommends raising the thermostat set point to 78 to 80 degrees while you're away, not turning the system completely off. This reduces runtime while preventing the thermal mass from fully loading with heat. The compressor's highest electrical draw occurs at startup and during initial pull-down from high temperatures. Forcing a 4-hour full pull-down from 85 degrees every evening during peak utility pricing hours, which typically run from 4 to 9 in the evening, is a reliable way to maximize your bill while minimizing your comfort window. Programmable and smart thermostats were engineered specifically to pre-cool your home before you arrive, using the window of time before peak pricing begins. The hack isn't turning it off. The hack is timing it correctly. 8. There is a smell. You're not sure what it is exactly, but it seems like it might be coming from the furnace area, and it's been going on for about 2 days. You've left the house running normally. You're calling to schedule a technician for Tuesday afternoon. Before this call ends, there is one thing that needs to be said with complete clarity. If you smell natural gas in your home, you do not call the HVAC company and schedule a Tuesday appointment. You leave the building immediately. You do not flip a light switch on your way out. You do not grab your phone from the charger. You do not stop to confirm the smell one more time. You go outside, you move away from the structure, and you call your gas utility's emergency line from outside. Natural gas is odorless in its original state. Mercaptan, specifically ethyl mercaptan, is added to it as a safety odorant at concentrations detectable by smell before the gas reaches dangerous levels. That smell exists because your utility company engineered it to make you leave the building. Natural gas becomes flammable at concentrations between 5 and 15% by volume in air. Any electrical arc, a light switch toggled, a thermostat clicking on, a phone charging on a counter, can ignite a gas-air mixture above that lower threshold. HVAC technicians are not equipped or authorized to diagnose active gas leaks. That is the jurisdiction of your gas utility, who will dispatch an emergency crew, shut off supply at the meter, and clear the structure before anyone else enters. This is not a Tuesday afternoon service call, this is an evacuation. If you've been smelling gas for 2 days and the house is still standing, you've been lucky. Do not continue pressing that luck until Tuesday. 9. The filter in your air handler has not been changed since last spring. You bought a 3-month filter. You checked it at the 6-month mark, decided it still looked acceptable, and you're calling now because the system has frozen solid and you cannot figure out what went wrong. What went wrong is sitting in the return air grill right now. A clogged air filter is the single most common cause of HVAC system failure across all equipment types and all climate zones, and the cascade of problems it creates is both predictable and expensive. Your system requires a specific volume of airflow across the evaporator coil to maintain safe operating temperatures. A heavily loaded filter can reduce airflow from the design specification to roughly half of what the coil needs, dropping the coil temperature below 32 degrees Fahrenheit and turning it into a solid block of ice, which then blocks all remaining airflow completely and shuts the system down. This is the call you're making right now. But here's the part that should genuinely concern you. If the system continues to operate with a frozen coil, liquid refrigerant gets pushed back to the compressor in a process called slugging, which can destroy the compressor valves within hours. A $10 filter left in place too long has now become a $1,500 to $2,800 compressor replacement. Filter replacement intervals depend on the filter type. Fiberglass filters require replacement every 30 days. Standard pleated filters need changing every 60 to 90 days. Homes with pets or smokers should change filters every 30 days, regardless of type. A dirty filter is also a reservoir of captured particulates that releases concentrated allergens back into the airstream when airflow velocity is high. Your indoor air quality suffers, your equipment suffers, and one Tuesday afternoon, you discover the system is a block of ice and cannot understand why. 10. There is water dripping from your air handler in the attic. You've examined the situation, done some reading, and arrived at a conclusion. Refrigerant leak. Refrigerant has to go somewhere, you've reasoned, and liquid is coming out, so the logical inference is that the refrigerant is leaking out as liquid. The technician who shows up is going to tell you the same thing every technician tells every customer who calls about this. That is condensation, not refrigerant. Refrigerant operates under pressure as either a high-pressure liquid within the sealed circuit or a low-pressure gas, and it does not drip onto your attic floor under any normal failure condition. What you're looking at is water, produced by the exact same physical process that makes a cold glass sweat on a humid summer afternoon. Your evaporator coil chills the refrigerant to approximately 40 degrees Fahrenheit. Warm, humid indoor air passes over that cold coil. Moisture condenses on the surface, and it drains through a condensate drain line. That drain line is typically a 3/4-inch PVC pipe that runs to a floor drain, utility sink, or exterior outlet. Algae, mold, and debris routinely clog it. The water backs up into the drain pan, and the pan overflows. This is the most common cause of water damage from attic-mounted air handlers in the country. It is not mysterious, and it is not a refrigerant issue. The clogged condensate drain line can be cleared with a wet-dry vacuum, a flush of distilled vinegar, or a condensate drain treatment tablet, and the entire process costs under $5 if you do it yourself. The catastrophic version of this problem, which is what happens when nobody clears the drain, is a saturated attic, a collapsed ceiling, and a repair bill that starts at several $1,000s and climbs from there. 11. You went to the hardware store with a specific mission, maximum air filtration. You found the filter display, identified the highest MARVI rating available, purchased it with the confidence of someone who just made an objectively correct decision, and installed it. Your system has been struggling for 3 weeks, and you'd like to know what's wrong with it. What's wrong with it is the filter you're so proud of. Your residential HVAC system was engineered to pull air through a filter within a specific resistance range. Most residential equipment is designed for filters rated between MRV6 and MRV13. A MRV16 filter, the kind found in hospitals and commercial clean rooms, has an extremely dense fiber matrix that creates airflow resistance. Your residential blower motor was never designed to overcome. The jump in restriction from MRV13 to MRV16 is not incremental, it is exponential. Your blower motor is now drawing higher amperage fighting that filter, running at elevated temperature and wearing out its internal components at an accelerated rate. Motor replacements run between $400 and $900. Meanwhile, the reduced airflow is dropping your evaporator coil temperature toward freezing and loading your filter faster than its rated interval, which compounds the restriction further. ASHRAE recommends MRV13 as the practical upper limit for residential forced air systems and has published explicit guidance warning against high MRV filters in equipment not designed for the resistance. If you genuinely need higher grade air filtration for medical or allergy reasons, the correct solution is a dedicated whole home air purification unit installed in the duct system with its own airflow path, not a filter that chokes the only path air has through your home. The intent was correct. The application destroyed what you were trying to protect. 12. The house is warm, and you want it to be cooler, and you want it there immediately, so you've set the thermostat to 60 degrees because obviously setting it lower will make the system work harder and cool the house faster. This is a belief held by a surprising number of adults who otherwise operate heavy machinery and manage financial accounts. Your central air conditioning system has one cooling mode, full capacity. There is no higher gear unlocked by a more aggressive set point. The compressor runs at full output whether the thermostat calls for 60 degrees or 72 degrees, and the rate at which your home cools is determined entirely by the system's BTU capacity relative to the thermal load of the structure. Setting the thermostat to 60 instead of 72 does not make the air colder, does not make the fan spin faster, and does not make the compressor work harder. It makes the system run longer because it now has to achieve a set point 12 degrees lower than where you actually want to be. And if you fall asleep on the couch and forget about it, you wake up to a 58-degree house and a compressor that has been running continuously for 6 hours. The single-stage AC compressor, which is the dominant type in residential homes, operates at 100% capacity or zero. There is no partial speed mode triggered by urgency. The rate of temperature change in a given home is a fixed physical relationship between equipment capacity and thermal load. It cannot be altered by how low you set the number on the wall. Variable speed equipment does modulate output, but it achieves better efficiency at small temperature differentials, not large ones, which is the exact opposite of what the overshoot strategy assumes. Set the thermostat where you want the house, leave it there. The house arrives at the same time either way. 13. You heard a clicking sound when the system tried to start. Twice. You consulted the internet, which confirmed your worst fears. The compressor is failing, the entire system is compromised, and you've already called 3 companies for replacement quotes. You're calling this technician as a professional courtesy before you commit to spending $12,000. The clicking noise you heard is almost certainly a failed capacitor. A capacitor. It is a cylindrical component approximately the size of a large can of soup. It costs between $15 and $40, and an experienced technician replaces it in roughly 10 minutes. Capacitors store and release electrical charge to start and run both the compressor motor and the condenser fan motor. Your outdoor unit almost certainly contains a dual-run capacitor serving both components. They degrade over time, primarily because the outdoor condenser unit sits in ambient temperatures that can exceed 130 degrees Fahrenheit on summer afternoons. And capacitor lifespan under those thermal conditions is typically 5 to 10 years. When the capacitor fails, the compressor attempts to start, draws locked rotor amperage, which is sometimes 4 to 6 times the normal running amperage, for a fraction of a second, fails to start, and the contactor and overcurrent protection circuit produces an audible click. The system resets, the process repeats. What you heard was not a compressor dying, it was your capacitor announcing its retirement. Here's the part that turns an inexpensive repair into an expensive one. Repeatedly allowing a system to attempt starting without a functioning capacitor stresses the compressor windings over time. And if you wait long enough doing nothing while collecting quotes for system replacement, the $40 repair eventually becomes the $1,500 repair you were afraid of in the first place. The clicking is real. The diagnosis it implies is not. 14. The ductwork in your crawl space has come apart at a joint. You handled it yourself. You went to the hardware store, purchased the most logically named product available for the task, wrapped the joint with it twice, and you'd like the technician to take a look at your work while they're here for the tune-up. The product you purchased is called duct tape. The job you used it for is the one job that duct tape, despite its name, was specifically not designed to do. Duct tape, the cloth-backed rubber adhesive variety sold in hardware stores, fails in the temperature and humidity conditions inside an HVAC duct system within 1 to 2 years. Lawrence Berkeley National Laboratory studied this extensively and found that standard duct tape failed in duct system conditions in virtually every test case, while appropriate alternatives maintain integrity for the duration of the study. The name duct tape derives from its original military application during the Second World War, sealing ammunition cases. It has nothing to do with HVAC ductwork, and the fact that the name stuck has been generating callbacks for technicians ever since. The correct product for duct sealing is UL 181 rated foil tape, a silver aluminum-backed pressure-sensitive tape that Underwriters Laboratories has formally approved for use in duct systems. The gold standard is mastic sealant, a flexible fiber-reinforced paste brushed over duct joints that is specifically referenced in energy codes for new construction and renovation projects. The Department of Energy estimates that duct leakage accounts for 20 to 30% of total HVAC energy loss in the average American home. Sealing ducts correctly is one of the highest return on investment home energy improvements available. The product named after the job cannot actually do the job. Use the product without the name recognition. It works. 15. Winter arrived and you protected your outdoor condenser unit with the thoroughness of someone who takes pride in property maintenance. You wrapped it in a heavy tarp, secured it with bungee cords, placed a wooden board on top weighted with a brick, and you sealed the whole thing so thoroughly that nothing could get in. Something got in. Several things got in. They nested in there over the winter and chewed the wiring, and now it's April and the system isn't starting, and you'd like someone to explain what happened. Outdoor condenser units are rated equipment. They are designed by manufacturers to withstand rain, snow, ice, and sustain freezing temperatures without protection because they are built to live outside permanently. What a fully enclosed tarp creates is not a protective environment. It is a warm, dark, sheltered space with accumulated debris and no airflow, which is a description that reads identically to the preferred winter habitat of every rodent in your zip code. Mice, chipmunks, and squirrels actively seek exactly this kind of enclosure for cold season nesting. Rodent-chewed wiring is one of the most common spring startup failures in cold climate areas, and it typically runs several hundred to over $1,000 to repair, depending on what was accessed. The full enclosure also traps moisture with no path to dissipate, saturating electrical components, contactors, capacitor housings, and copper connections over the course of a winter. If you want to protect the top of the unit from falling ice or direct hail impact, a partial top cover that leaves all four sides completely open accomplishes that without creating an enclosure. Heat pump units must never be covered under any circumstances, as they operate year-round and require continuous airflow. The manufacturer documentation for your unit says not to cover it. The warranty may not cover rodent damage to an improperly stored unit. 16. You've been running the system fan in on position for air circulation, your skin has been feeling dry, and you've concluded the air conditioning is over-dehumidifying the home. You'd like a whole home humidifier added to the duct system before the weekend. There are two separate problems with this request. First, the continuous fan operation is actively raising your indoor humidity, as covered earlier in this list, so the dryness you're experiencing is almost certainly not from insufficient moisture in the air. Second, adding a humidifier to a forced air system during summer in any climate with outdoor dew points above 60 degrees Fahrenheit risks pushing indoor relative humidity above the threshold where mold colonizes surfaces. ASHRAE recommends indoor relative humidity of 30 to 50% for both comfort and air quality. In most U.S. climates during summer, a properly air-conditioned home sits between 45 and 55% relative humidity, which is comfortably within the recommended range for the majority of occupants. Whole home bypass humidifiers are designed specifically for winter heating operation. They add moisture to air that has been severely dried out by the furnace heating cycle during cold months when outdoor humidity is naturally low. Operating one during summer cooling season in a climate with outdoor air already carrying significant moisture content is a reliable way to create the exact mold problem you don't currently have. Dry skin in summer can be caused by pool chemicals, soap formulation, dehydration, medication side effects, and a dozen other variables, none of which are solved by increasing indoor humidity. The correct tool for diagnosing this is an accurate RH measurement taken inside the home, not a symptom guess made while running continuous fan operation. Measure before you add equipment. The answer might be to stop doing something rather than to start. 17. You've walked every room in the house and pressed your hand up to every supply vent, airflow from all of them. You've concluded the duct system is sealed, balanced, and performing at full capacity. You would like the technician to look somewhere else. Feeling airflow from a supply register confirms one thing. The blower is running and the duct leading to that register is not completely collapsed. That is the full scope of diagnostic information your palm can provide. It tells you nothing about duct leakage, airflow volume, air balance between rooms, static pressure, or system efficiency. You can lose 30% of your conditioned air into the attic through duct leakage and still feel airflow at every single register because the register is downstream of the leak and is receiving whatever volume of air made it past the breach. Duct leakage is measured with a blower door test or a duct blaster test, both of which pressurize the duct system and measure the rate of air escaping through breaches. The Department of Energy and the EPA estimate that 25 to 40% of conditioned air is lost through duct leakage in a typical home. The customers at every one of those homes would also report feeling air at the vents. Supply-side duct leaks on the pressurized side of the blower push conditioned air directly into wall cavities, unconditioned attic space, and crawl space, completely bypassing your living area, while the register still shows detectable flow. Air balance, the distribution of correct airflow volume between rooms relative to their individual thermal loads, requires measurement with a flow hood or anemometer at each register. A system can be dramatically undersized for the equipment it serves, creating performance deficits that show up on your energy bill and in your comfort level, while every single vent produces detectable airflow. Your hand is not a diagnostic instrument. 18. Your air conditioner smells like a locker room every time it starts up. You've addressed this with a full can of aerosol air freshener sprayed directly into the return vent, 4 plug-in deodorizers, and a conversation with a neighbor who suggested maybe it's just an old system. The smell has a name in the HVAC industry. It is called dirty sock syndrome, and it is a documented, categorized phenomenon caused by microbial growth, specifically bacteria and mold, colonizing the damp surface of your evaporator coil and drain pan. The odor is most intense at startup because that's when airflow disturbs the biofilm on the coil surface and carries its volatile organic compounds into your living space. It dissipates after the system has been running for a few minutes, which is why it feels intermittent and why you've tolerated it for longer than you should have. Systems that are oversized and short cycle, which you may remember from item 4, are significantly more prone to this condition because the coil never runs long enough to fully dry between cycles, maintaining the wet surface that biological growth requires. The treatment is a professional coil cleaning with a foaming coil cleaner, followed by a drain pan treatment with antimicrobial tablets, and optionally a UV germicidal lamp installed inside the air handler to continuously suppress biological growth on the coil surface. Studies show that UV germicidal lamps maintain coil cleanliness and can improve system efficiency by 10 to 15% by preventing the insulating effect of biofilm accumulation. Now, about that aerosol air freshener you sprayed into the return vent. The fragrance chemicals in that product have coated your evaporator coil with a film that serves as an additional food source for bacterial growth, which means you have actively made this problem worse while making the house smell briefly like a pine forest over a locker room. The coil needs to be cleaned professionally. Stop feeding the biofilm. 19. Your carbon monoxide detector has alarmed twice this week, and you've resolved the situation by pulling the battery out because it kept going off for no reason. And you're calling now to ask whether the furnace can produce carbon monoxide and whether you should be concerned. You are currently inside the home. Here's what needs to be communicated before anything else in this conversation. A carbon monoxide detector that alarms is not malfunctioning. It is detecting carbon monoxide. Those are different events with different appropriate responses, and the appropriate response to the second one is not to remove the battery and go back to whatever you were doing. Carbon monoxide binds to hemoglobin in your blood approximately 200 to 250 times more readily than oxygen does. It forms a compound called carboxyhemoglobin that prevents oxygen transport entirely. Symptoms begin at blood saturation levels as low as 10%, and unconsciousness can occur at 50 to 70% saturation, at which point you are no longer in a position to call anyone. The CDC estimates approximately 400 Americans die from unintentional, non-fire-related CO poisoning annually, with roughly 100,000 emergency room visits per year, making it the leading cause of accidental poisoning death in the United States. CO detectors are calibrated to alarm at sustained concentrations of 70 parts per million over 1 to 4 hours, or 400 parts per million over 4 to 15 minutes. These thresholds are designed to protect you before symptoms become obvious, because the gas itself is colorless and odorless and will give you no independent warning. The correct response to a CO alarm is to evacuate immediately, leave the door open, call 911 from outside, and not re-enter until the fire department has cleared the structure with a combustion analyzer. That is the protocol. The battery goes back in when the building is declared safe, not before. 20. You purchased a mini split system online. You've watched several installation videos. You've already mounted the indoor head and run the line set through the wall, and you're calling to find out where you can purchase refrigerant to charge the system yourself. You sound confident. Before this goes further, there are two separate problems, and the legal one comes first. Purchasing and handling refrigerant in the United States requires an EPA Section 608 certification under the Clean Air Act. R410A, the refrigerant in most current residential equipment, carries a global warming potential of 2088 and falls squarely within the regulated category. Violation of Section 608 carries civil penalties up to $44,539 per day per violation. You cannot buy it at the hardware store. There's a reason for that. The second problem is what happens to the system if you somehow obtained refrigerant and added it without proper preparation. Before any refrigerant system is charged, the line set and indoor coil must be evacuated to below 500 microns of pressure using a dedicated vacuum pump and micron gauge to remove all residual air and moisture. Air and moisture trapped in a refrigerant circuit react with the refrigerant and the compressor oil to form acids that destroy compressor valve seats from the inside. This damage is not immediate and dramatic. It is quiet and cumulative, and it presents as a failed compressor 1 to 3 seasons later with no obvious explanation. Most mini-split manufacturer warranties explicitly void all coverage for any system not installed by a licensed contractor. The flare connections on the line set require a precision flaring tool and specific torque values. An improperly made flare is the leading cause of refrigerant leaks in amateur installations. The videos were informative. They were not a license to proceed. 21. The supply air from your vents feels cold, so you've concluded the refrigerant charge is fine, and you'd like the technician who just finished taking gauge readings to stop recommending a leak check and focus on something else. Your hands are not a refrigerant diagnostic instrument. A system can be 20 to 30% undercharged on refrigerant, and still produce supply air that registers as cool against your palm, because the air coming from the registers will still be below room temperature even when the system is operating significantly outside its specified parameters. The only way to verify refrigerant charge is to connect a gauge manifold to the surface ports and measure suction pressure, discharge pressure, and either superheat or subcooling values. Then compare those readings against manufacturer specifications for the current outdoor ambient temperature and indoor wet bulb temperature conditions. A system that is 10 to 15% undercharged shows reduced suction pressure, elevated superheat, and reduced total system capacity, but may still produce supply air that is 15 to 20 degrees below room temperature. Cool enough to feel cold, not correct enough to be healthy. An undercharged system runs longer cycles to meet the same cooling load, increasing runtime, electricity consumption, and compressor operating hours, while simultaneously providing inferior dehumidification because the coil never reaches optimal condensing conditions. And here's the other direction of the same mistake. An overcharged system, meaning too much refrigerant has been added, is equally damaging. Excess liquid refrigerant can enter the compressor in liquid form, a condition called slugging, and destroy the compressor in a single operating event. Overcharging is the predictable outcome of adding refrigerant without proper gauge measurement, which is what happens when the diagnostic approach is to feel the air and conclude everything is acceptable. The gauges exist because the alternatives are expensive. 22. You installed a programmable thermostat 6 months ago, your electricity bill has not changed, and you want to know if the unit is defective. You set it to the energy-saving preset mode and left it there. You have not touched the programming since installation. The thermostat is not defective. The factory default schedule on most programmable thermostats is set to maintain comfort temperatures 24 hours a day, 7 days a week, across both weekdays and weekends. That is functionally identical to a manual thermostat left at a fixed setting, which produces zero savings over a manual thermostat left at a fixed setting. A programmable thermostat saves energy only if it is programmed with a schedule that reflects your household's actual occupancy and includes meaningful temperature setbacks during periods when the home is unoccupied or you are asleep. The EPA's Energy Star program estimates that a properly programmed thermostat can reduce heating costs by approximately 10 to 12% and cooling costs by approximately 15% annually. But the phrase properly programmed is carrying all the weight in that sentence. The mechanism is straightforward. The Department of Energy estimates that for every degree of setback maintained for 8 hours, approximately 1% of daily heating or cooling energy is saved. A 10-degree setback for 8 hours is roughly 10% savings for that period. That math requires you to program a schedule. There's also the override problem, which is the other way this fails. You program a schedule, then manually override it every morning based on how you feel, and the automation is defeated entirely before it saves a single dollar. Smart thermostats with occupancy sensors address this by learning your patterns, but they require an initial learning period and correct sensor placement to function as intended. The tool saves money when you use the tool. A thermostat set to factory defaults and left alone is just a more expensive version of the manual thermostat you replaced. 23. Your basement has uninsulated sheet metal ductwork, and when asked about adding insulation, you've pointed out that the ducts are inside the house and the house is air conditioned. So why would insulation be necessary for ductwork that already exists inside a conditioned environment? Your basement is almost certainly not a conditioned environment in any meaningful sense. In most residential construction, the basement, crawl space, and attic are outside the thermal envelope of the home, meaning they are not actively conditioned spaces. They fluctuate with outdoor temperatures, sometimes dramatically. A basement in winter can drop to 45 to 55 degrees Fahrenheit. When supply air travels through uninsulated sheet metal ductwork in a 50-degree basement, that air loses heat to the surrounding cold environment before it ever reaches the register in the living space, arriving at a lower temperature than it left the furnace. The reduction can reach 5 to 15 degrees depending on duct length and ambient conditions. In summer, the situation reverses. Attic temperatures reach 140 to 160 degrees Fahrenheit, and supply air in uninsulated attic ductwork gains heat from the surrounding space, arriving at the register warmer and less effective than when it left the air handler. The Department of Energy recommends a minimum of R6 insulation on all ductwork in unconditioned spaces, and this requirement is codified in the International Energy Conservation Code for new construction. There is also a moisture problem. In humid conditions, uninsulated cold supply ductwork in a warm basement environment drops below the dew point of the surrounding air, causing condensation on the exterior duct surface. Over time, this produces corrosion, exterior mold growth, and ceiling damage in finished basements with overhead ductwork. The duct is inside the building. The building has multiple temperature zones. The physics does not stop at the basement stairs. 24, nothing is broken. The system runs. You've declined the annual maintenance agreement for 5 consecutive years on the basis that nothing is broken, and therefore maintenance is not a necessary expenditure. You're calling today because the system stopped working this morning. Annual HVAC maintenance is not a service designed for systems that are already broken. It is designed to find the things that are quietly failing before they cause the event you are currently experiencing. A capacitor degrading from its rated microfarad value toward failure produces no symptom visible to a homeowner without instruments until the moment it fails completely. At that point, the compressor draws locked rotor amperage repeatedly, stressing the compressor windings, and what was a $40 capacitor replacement on a maintenance visit becomes a $1,500 to $2,800 compressor replacement if the degraded capacitor was left in place long enough. Condenser coil fouling from accumulated dust, cottonwood, and debris reduces heat rejection efficiency by 10 to 30% and is not visible from normal observation distance. A heat exchanger crack requires the furnace panels to be removed and the exchanger examined under light at operating temperature. Refrigerant charge verification requires gauge manifold readings. None of these are visible to an untrained homeowner without instruments, which is precisely why the visit exists. The Air Conditioning Contractors of America found that systems receiving annual preventive maintenance fail at approximately 40% lower rates over a 10-year period compared to unmaintained systems. Most manufacturer extended warranties, the 5 to 10-year parts coverage that comes with new equipment, require documented annual maintenance by a licensed technician as a condition of coverage. Skipping maintenance can void a warranty claim on a repair that would otherwise have cost you nothing. The 5 years of declining the service agreement are the explanation for this morning's call. 25. Your outdoor condenser unit is surrounded on 3 sides by a dense hedge, enclosed on the 4th side by a decorative privacy fence, and you've installed a lattice roof structure overhead to soften the visual impact of the equipment on the garden aesthetic. The system has not worked properly since June, and you'd like the technician to look at the equipment while they're here. The technician is going to find the problem immediately upon walking into your backyard. A condenser unit rejects heat from your home to the outdoor environment by pulling large volumes of ambient air through its coil using the condenser fan. Most residential units move between 1,000 and 2,500 cubic feet per minute of air through that coil continuously during operation. This process requires unrestricted access to ambient outdoor air on all intake sides and completely unobstructed exhaust from the top of the unit. Most manufacturers specify a minimum clearance of 18 to 24 inches on all sides and 48 to 60 inches above the unit. What you have built is a heat trap. When the condenser unit cannot access ambient air and instead recirculates the hot exhaust it just produced, head pressure rises. Elevated head pressure increases the compression ratio the compressor must work against, raises amperage draw, generates additional internal heat, and accelerates wear on every component under load. Sustained operation at elevated head pressure compresses lubricating oil in the compressor beyond its optimal viscosity range, accelerating bearing wear until the compressor fails. High head pressure also triggers the high pressure limit switch, which is why your system shuts off on hot days. The correct landscaping within the equipment clearance zone is low ground cover or mulch. Any screening hedge or fence maintained at no less than 3 feet from the unit on all sides. Several landscape design resources publish HVAC compatible guidelines specifically because this scenario is common enough to warrant documentation. 26. You're running 4 window air conditioning units throughout your 2,400 square foot 2-story home because central air conditioning is overkill for a house your size, and you're calling about your electricity bill, which has climbed to a level that no longer seems reasonable for a strategy you adopted specifically to save money. The 4 window units are the electricity bill. Window air conditioners typically carry SEER ratings of 10 to 12, and older residential units often score lower than that. Modern central air conditioning systems operate at 14 to 20 SEER. Current mini-split systems routinely achieve 20 to 30 SEER. What SEER means in practical terms is how much cooling you get per unit of electricity consumed. A system at 20 SEER delivers the same amount of cooling for roughly 40 to 50% less electricity than a system at 10 SEER. You are running 4 separate compressors, 4 separate condenser fans, and 4 separate evaporator fans, all operating at the low end of the efficiency spectrum simultaneously. 4 standard 12,000 BTU window units running at the same time draw approximately 18 to 22 amperes continuously, which is comparable to or greater than the running load of a 3-ton central system while delivering a fraction of the efficiency. Central systems also dehumidify the entire home through a single properly sized coil. Window units dehumidify the immediate room and leave adjacent spaces at whatever humidity the outdoor environment provides. Air distribution from a window unit is localized to the area directly in front of the unit, with the far corners of even a moderate-sized room remaining warmer and less comfortable. Window units introduce security vulnerabilities, seal degradation around the frame, and noise that a central or mini-split system does not. The strategy was reasonable on a single unit basis. 4 units running continuously in a large home is not the savings calculation you were working from. 27. You come home to a cold house in January. You set the thermostat to 80 degrees because you want to reach 70 degrees as quickly as possible. And you've been doing this your entire adult life under the impression that you've discovered a personal efficiency technique. The house heats at the same rate whether you set the thermostat to 70 or 80. This is not a variable. A gas furnace outputs heat at a fixed rate determined by its BTU capacity, for example, 80,000 BTU per hour, and that output does not change based on the size of the differential between the current indoor temperature and the thermostat set point. The time required to raise the indoor temperature from 62 degrees to 70 degrees is identical whether the set point is 70 or 80. The furnace runs at the same capacity. The thermostat is simply an on and off switch. When the measured temperature at the thermostat reaches the set point, the furnace shuts off. A higher set point means the furnace runs longer total, not faster or harder. 2-stage and modulating furnaces actually behave in the opposite direction of what this strategy assumes. They produce less heat output during mild conditions to avoid overshooting the set point, not more. Setting the thermostat to 80 and correcting back to 70, once you've warmed up, creates a thermal overshoot cycle that makes the average indoor temperature less stable and less comfortable than simply setting an accurate target and leaving it alone. Smart thermostats with adaptive recovery algorithms solve the problem you're actually trying to solve. They calculate how long the system needs to reach the set point and begin heating proactively so the house is at your preferred temperature when you arrive without requiring you to overshoot. You are not making the house warm faster, you are making the furnace run longer and the house less stable. Set the correct number. 28. Your furnace is short cycling, meaning it runs for a few minutes and shuts off repeatedly. You've Googled this. The internet has delivered a verdict. Cracked heat exchanger, replace the entire furnace. You've priced new furnaces. You're ready to proceed. Before you spend $10,000, work through the actual diagnostic sequence that a technician applies to a short cycling furnace in order of probability. First, check the air filter. A clogged filter restricts airflow, causes the heat exchanger to overheat, triggers the high limit switch, which shuts the burner off, and the cycle repeats exactly as you've described. This is the most common cause of furnace short cycling. Second, check the flame sensor. The flame sensor is a small rod that detects the presence of the burner flame. When coated with oxidation, which happens over time, it fails to sense the flame accurately and shuts off the gas within seconds of ignition. Cleaning the flame sensor requires removing one screw, sanding the rod lightly with fine steel wool, and reinstalling it. This is a 10-minute task. Third, check for blocked registers or a closed return vent, both of which produce the same airflow restriction as a clogged filter. Fourth, test the high limit switch itself for failure in the tripped position. Fifth, and only after the previous four have been ruled out, inspect the heat exchanger for cracks. A cracked heat exchanger is a legitimate safety concern because it can allow combustion gases including carbon monoxide to enter the airstream. It is also diagnosed by visual inspection with a combustion analyzer at operating temperature, not by a symptom alone. The symptom you have is consistent with a $5 filter change and a 10-minute flame sensor cleaning. Proceeding directly to furnace replacement from a short cycling diagnosis is not a reasonable skip in the sequence. 29. Your house is consistently hot upstairs in summer and cold upstairs in winter. You've had the HVAC system serviced 4 times this year, and the upstairs still doesn't hold temperature, so you're calling to have the equipment checked again. The technician who showed up the first 3 times was looking at the right equipment. The problem you're describing is an insulation problem, not an equipment problem. The HVAC system can only condition the air inside the thermal envelope of the building. If that envelope has insufficient insulation, the system cannot compensate for the heat transfer occurring continuously through under-insulated surfaces. The Department of Energy's current recommendation for attic insulation is R49 to R60 in most U.S. climate zones. Homes built before 1980 commonly contain R11 or less in the attic assembly, which is approximately 20 to 25% of the insulating value the space requires. An attic in summer reaches 140 to 160 degrees Fahrenheit. With R11 separating that attic from your upstairs ceiling, radiant and conductive heat transfer from above adds the equivalent of 1 to 3 tons of additional cooling load to your upper floor. Load that the air conditioning system removes continuously, only to have it immediately replaced by the next wave of heat transfer through the ceiling. The system runs, the upstairs stays warm, and the equipment gets serviced repeatedly for a condition it cannot resolve. Air sealing matters equally. Gaps around light fixtures, plumbing penetrations, and framing at the attic floor level allow warm attic air to infiltrate directly into the living space regardless of how much insulation sits above those gaps. The DOE estimates that adding attic insulation from R11 to R49 with proper air sealing can reduce heating and cooling costs by 10 to 20%. Service the building before you service the equipment again. 30. You noticed a sweet smell near the outdoor condenser unit last Tuesday. You assumed it was a neighbor's flowering hedge. It is now Saturday, the smell is still present, and you mentioned it almost as an afterthought at the end of a call about scheduling a routine tune-up. The sweet, faintly chemical odor near an outdoor condenser unit is not a flowering hedge. It is a classic indicator of refrigerant leaking from the system, and by the time you can smell it, you already have a meaningful leak. R410A, the dominant residential refrigerant from approximately 2010 through the current transition period, has a faint sweet odor that is detectable at concentrations well above the level that begins to affect system performance. You have been operating on a reduced refrigerant charge for at least 4 days, possibly longer. R410A operates at significantly higher pressures than older refrigerants, with high side pressures reaching 400 to 600 psi. At those pressures, leaks from damaged service ports, faulty Schroeder valves, or vibration-fatigued joints in the line set can lose charge faster than lower pressure systems. As the refrigerant charge drops below the manufacturer's specified operating range, suction pressure falls, the evaporator coil temperature drops toward freezing, and the compressor receives insufficient lubrication because refrigerant carries compressor oil through the circuit. Extended operation in this condition accelerates compressor wear toward failure. Refrigerant handling and leak repair requires EPA Section 608 certification and leak detection equipment. The Clean Air Act prohibits venting refrigerant to the atmosphere. Your technician will recover the remaining charge, locate and repair the leak, and recharge the system to the nameplate specification. R410A is itself being phased down under EPA regulations beginning in 2025 making refrigerant costs and availability an increasing factor in repair versus replace decisions on older systems. The sweet smell was not the hedge. It has not been the hedge all week. 31, you bought a new home 18 months ago, the HVAC has never worked well since you moved in, the upstairs is always too hot and the master bedroom is always too cold. The system runs constantly, but you're reluctant to push on it because the equipment is brand new and was presumably installed correctly. New construction. HVAC installation is one of the most consistently problematic categories in residential HVAC service. Ductwork is roughed in by installation crews working under significant time and cost pressure. Sizing decisions are frequently made by rule of thumb rather than manual J-load calculation, and commissioning, which is the process of testing and adjusting airflow, refrigerant charge, and system controls to verify performance matches design intent, is virtually never performed in residential new construction. A California Energy Commission study found that a significant percentage of new residential HVAC systems were either oversized, undersized, improperly charged, or had ductwork with measurable leakage rates exceeding code requirements. None of this is visible to a buyer at closing. The building permit required a load calculation in many jurisdictions, but the calculation is sometimes performed with software using default inputs rather than actual site measurements, producing systematically inaccurate sizing. The duct system was installed before drywall and sealed before anyone tested it, and duct leakage testing during construction, while required in some jurisdictions, remains far from universal in residential work. Airflow balancing, which is the process of adjusting dampers and register sizes to deliver the correct volume of air to each room based on its load, is almost never performed in residential new construction unless specifically contracted and paid for separately. The base time to identify and correct these deficiencies was during your builder's warranty period, which is typically 1 year for systems and 2 years for structural components. The equipment is new. The installation is a separate question entirely from the equipment's age. 32. Your ductwork makes a significant whistling or banging noise every time the system cycles on and off. You've lived with it for 3 years because your neighbor's house makes a similar sound, which you've taken as evidence that it's a normal characteristic of forced air systems. Significant duct noise is not normal. It is diagnostic. Every sound your duct system makes under operation is telling you something specific about what is wrong with the airflow. Whistling indicates excessive air velocity, which means air is being pushed through ductwork that is undersized for the system's airflow, partially blocked by a closed vent or a heavily loaded filter, or sized correctly for a smaller system than the one currently connected to it. Air velocity in correctly designed residential ductwork should be 600 to 900 feet per minute in main trunk lines. Velocities above 1,000 feet per minute produce the audible whistling you've normalized, along with increased static pressure and noise at the register diffusers. Banging and the metallic flexing sound called oil canning are caused by the duct walls moving under positive and negative pressure cycles, which means your static pressure is high enough that the sheet metal is being pushed outward and pulled inward with each system cycle. These are not comfort issues. They indicate measurable performance problems. Elevated static pressure reduces blower motor airflow, increases electricity consumption, and shortens motor lifespan, and the cause of that elevated pressure, whether it is closed vents from item 3, a clogged filter from item 9, or an undersized duct run, is something that can be diagnosed and corrected. Your neighbor's house makes the same sound. That means your neighbor also has a static pressure problem, not that the sound is acceptable. 2 households sharing a performance deficiency is not a reference point, it's 2 service calls that haven't been made yet. 33, your HVAC system is 12 years old, you've read that the average lifespan is 10 to 15 years, and you've scheduled a replacement appointment before the system fails. The system is currently operating correctly and has been maintained annually. A well-maintained HVAC system that is operating correctly has no defined replacement age. The 10 to 15 year average cited in consumer literature is a statistical average that includes poorly maintained systems, systems installed in extreme climates with high annual runtimes, systems that were improperly sized at installation, and systems that received no maintenance until they failed. It is the same kind of average that becomes meaningless when applied to a specific well-maintained example. A quality system with annual maintenance, clean coils, verified refrigerant charge, and timely capacitor and contactor replacement can operate reliably for 20 to 25 years. The economically rational replacement decision is based on repair cost relative to replacement cost, efficiency improvement, and its calculated payback period, and refrigerant platform sustainability, not on a round number appearing on a calendar. The 50% rule, widely cited in the industry, suggests that if the cost of a repair approaches 50% of the replacement cost of comparable new equipment, replacement becomes the more rational financial decision. At 12 years on a functioning maintained system, you are almost certainly not there. The major components with predictable age-dependent failure rates include capacitors and contactors, both inexpensive to replace on a maintenance schedule, and the compressor and heat exchanger, both of which fail on a usage and maintenance timeline rather than a calendar one. If the system's efficiency is measurably lower than current equipment and the payback calculation on a replacement is favorable, that is a legitimate reason to replace. Replacing a functioning system because the number 12 appeared in the maintenance record is not. 34, the technician left 45 minutes ago, the house is currently at 76 degrees, and you're calling back because you paid for a service call and the house is not at the 68-degree set point yet, and you'd like the technician to return. The system was repaired. The technician confirmed correct operating pressures, supply and return temperature differential within manufacturer specifications, and proper electrical function before leaving. What you are experiencing now is not a system malfunction. It is thermodynamics operating on a schedule that does not adjust for your preference. An air conditioning system that has been repaired and is operating correctly still requires time to remove the thermal load that accumulated in the building while the system was either malfunctioning or off. If the house reached 80 degrees or higher before the repair, the system must now cool not only the air, but every object in the home, the walls, the flooring, the furniture, all of which absorbed heat during the outage period. This is the thermal mass loading discussed in item 7, and it applies here in the same way. A 3-ton system removing heat from a 2,000 square foot home that has reached 82 degrees on a 95-degree outdoor day will typically require 2 to 4 hours to reach a 70-degree set point, accounting for the continuous heat gain from the outdoor environment occurring simultaneously. The correct diagnostic confirmation that the system was repaired successfully is not the house being at set point 45 minutes later. It is the system operating within manufacturer specifications at the time of departure, which the technician verified before leaving. If you measure the temperature differential between supply and return air right now, you will find it within the correct range. The system is working. Physics has a schedule that is not negotiable by callback. 35, you have a heat pump, it has been cold, and you switched the thermostat to emergency heat mode 3 weeks ago because you assumed it was the appropriate setting for when the weather gets seriously cold. Your electricity bill has tripled and you'd like to know if the heat pump is malfunctioning. The heat pump is not malfunctioning. The emergency heat mode is. Emergency heat bypasses the heat pump entirely and runs only the electric resistance backup strips, which operate at 100% efficiency, 1 unit of electricity in, 1 unit of heat out. A heat pump in heating mode operates at 150 to 300% efficiency depending on outdoor temperature, meaning it delivers 1.5 to 3 units of heat for every unit of electricity consumed, because it is moving heat from the outdoor air rather than generating it from electrical resistance. At an outdoor temperature of 32 degrees Fahrenheit, your heat pump's cube is still likely above 1.5, meaning it is still dramatically cheaper to operate than the backup strips you've been running exclusively for 3 weeks. Emergency heat exists for one specific scenario. The heat pump has physically failed and cannot operate, and you need temporary heat while it is repaired. It is not a cold weather boost setting. It is a backup mode for a broken primary system. The AUX heat indicator that appears automatically on your thermostat when outdoor temperatures drop and the system stages in the backup strips is normal and expected and is managed automatically by the equipment. Emergency heat is a manual override that removes the heat pump from the circuit entirely. Cold climate heat pump models maintain effective heating capacity at outdoor temperatures as low as -13 to -22 degrees Fahrenheit. Running backup strips exclusively in 30-degree weather on a functioning heat pump is paying 3 times more than necessary for heat your primary system was handling correctly before you intervened. 36. Your carbon monoxide detector keeps alarming and you've determined the cause. It's faulty. You've removed the battery. You've replaced it with a different unit that also alarmed. You've removed that battery too. You're calling the HVAC company because you've heard furnaces can sometimes do something with carbon monoxide, and you thought it worth mentioning while scheduling a filter change for next week. Both detectors alarmed. You replaced the first one, the second one alarmed, and the conclusion you reached was that the problem was the detector rather than the thing the detector was detecting. Carbon monoxide detectors do fail, but they fail by not alarming, not by producing repeated accurate readings at specific CO concentrations and then having those same concentrations confirmed by a second independent device. 2 separate detectors alarming in the same home is not a detector problem. It is a CO problem with 2 witnesses. You are currently living in a home with confirmed carbon monoxide at concentrations sufficient to trigger 2 independent detection devices with no functioning detector present because you've removed both batteries. This is the call that ends the conversation about scheduling. You leave the building now. You call 911 from outside. You do not go back in to get your phone, your keys, or your shoes. The furnace is the most likely source, specifically a cracked heat exchanger allowing combustion gases to enter the airstream, a blocked flue preventing exhaust gases from venting outdoors, or an improper combustion air-to-fuel ratio. All of these are diagnosable and repairable. None of them can be diagnosed while you are inside the building with no functioning detector. The filter change is not happening next week until this is resolved today. Put the battery back in neither detector. Put yourself outside and call for help. 37. You watched a tutorial online, purchased a mini split system through an internet retailer, mounted the indoor head, ran the line set through the wall, and you're calling to ask where to buy refrigerant so you can finish the job yourself. There are 2 distinct problems here, and the legal one arrives first. Purchasing and handling refrigerant in the United States requires an EPA Section 608 certification under the Clean Air Act. R410A, the refrigerant in most current residential equipment, carries a global warming potential of 2088 and is fully within the regulated category. You cannot purchase it at a hardware store or home improvement center. That restriction exists specifically because the next problem is what happens when someone who hasn't been trained handles it. Before any refrigerant system is charged, the line set and indoor coil must be evacuated to below 500 microns using a dedicated vacuum pump and micron gauge to remove all residual air and moisture. Air and moisture trapped in a refrigerant circuit react chemically with the refrigerant and compressor oil to form acids that destroy compressor valve seats from the inside over 1 to 3 seasons of operation. The damage is invisible and cumulative. The flare connections on your line set require a precision flaring tool and specific torque values at each fitting. An improperly made flare is the leading cause of refrigerant leaks in amateur mini-split installations, and a leak that develops at the flare means you've lost whatever refrigerant was in the system and the compressor has been running with insufficient lubrication. Most manufacturer warranties explicitly void all coverage for systems not installed by a licensed contractor, which means the equipment you purchased online is currently unwarranted and uncharged. The videos were thorough. They were not a substitute for the certification, the vacuum equipment, or the legal authority to complete this installation. 38. The air from your supply vents feels cold, and on the basis of that tactile assessment you've concluded the refrigerant charge is acceptable, and the technician currently holding a gauge manifold at your service ports should redirect their attention elsewhere. Your hands have never successfully diagnosed a refrigerant charge. A system operating 20 to 30% below its specified refrigerant charge will still produce supply air that registers as cool against your palm, because the temperature differential between conditioned supply air and room temperature remains perceptible even when the system is working significantly outside its design parameters. The only method for verifying refrigerant charge is measuring suction pressure, discharge pressure, and either superheat or subcooling at the service ports and comparing those values against manufacturer specifications for the current outdoor ambient temperature and indoor wet bulb conditions. An undercharged system shows reduced suction pressure and elevated superheat. It runs longer cycles to meet the same cooling load, consuming more electricity and accumulating more compressor operating hours, while providing inferior dehumidification because the coil never sustains the condensing conditions required for effective moisture removal. The efficiency loss from a 10 to 15% refrigerant deficit is measurable on your monthly utility bill, even when the supply air still feels cool enough to satisfy a hand test. The overcharged direction is equally damaging and arguably more immediate. Excess liquid refrigerant entering the compressor in liquid form destroys the compressor valve plates in a single operating event called slugging. Overcharging is the predictable result of adding refrigerant without measuring first, which is exactly what happens when the diagnostic process consists of feeling the air and declaring everything acceptable. The gauge manifold in the technician's hand costs less to use than any of the repairs that follow from not using it. 39. You installed a programmable thermostat 6 months ago, your electricity bill has not decreased, and you're calling to report a defective unit. You set it to the energy-saving preset, have not adjusted any programming since installation, and would like a replacement sent out. The thermostat is functioning correctly. The factory default schedule programmed into most residential programmable thermostats maintains comfort temperatures 24 hours a day across all 7 days of the week. That schedule produces identical energy consumption to a manual thermostat left at a fixed setting, because it is functionally identical to a manual thermostat left at a fixed setting. A programmable thermostat reduces energy consumption only when programmed with a schedule that includes meaningful temperature setbacks during periods when the home is genuinely unoccupied or you are sleeping. The EPA's Energy Star program estimates properly programmed thermostats reduce heating costs by 10 to 12% and cooling costs by approximately 15% annually. The operative phrase in that sentence is properly programmed, which requires you to open the scheduling menu and input your household's actual occupancy pattern with deliberate setback temperatures. The Department of Energy's calculation is straightforward. Each degree of setback maintained for 8 hours saves approximately 1% of that period's heating or cooling energy. A 10-degree setback held for 8 hours saves roughly 10% of that window's consumption. That result requires a programmed schedule. There is also a second failure mode that negates the first. Manually overriding the schedule each day based on how you feel defeats the automation before it produces $1 of savings. Smart thermostats with occupancy sensors address the programming burden by learning your patterns, but they require a learning period and correctly placed sensors. A programmable thermostat running on factory defaults is a $40 digital clock attached to your HVAC system. Program the schedule. 40. Your basement has uninsulated sheet metal ductwork running across the ceiling, and your position is that since the ducts are physically inside the house, insulation serves no purpose because the surrounding air is conditioned. Your basement is not a conditioned space in the way you're imagining. In most residential construction, the basement exists outside the active thermal envelope of the home. It receives incidental conditioning through duct losses and door infiltration, but it is not a space maintained at a controlled temperature by design. In winter, an unconditioned basement can drop to 45 to 55 degrees Fahrenheit. Supply air traveling through uninsulated sheet metal in that environment loses heat to the surrounding cold before it reaches the register in the living space above. That temperature loss reaches 5 to 15 degrees depending on duct length and ambient conditions, meaning the air your furnace heated to 120 degrees may arrive at your bedroom register at 105 degrees. In summer, attic temperatures reach 140 to 160 degrees Fahrenheit, and supply air in uninsulated attic ductwork gains heat from the surrounding space, arriving warmer and less effective than it left the air handler. The Department of Energy recommends a minimum of R6 insulation on all ductwork in unconditioned spaces, codified in the International Energy Conservation Code for new construction. Condensation is the other problem. In humid conditions, cold supply air in an uninsulated duct drops the exterior duct surface below the dew point of the surrounding basement air, producing condensation on the exterior of the duct. Sustained condensation causes corrosion, exterior mold growth on duct surfaces, and ceiling damage in finished basements with overhead ductwork. The duct is inside the building envelope. The basement temperature is not. The physics does not reorganize itself to accommodate your floor plan. 41. Nothing has broken. You've declined the annual service agreement for 5 consecutive years, specifically because nothing has broken, and the absence of a failure has served as confirmation that no maintenance is required. You are calling this morning because the system stopped working. Annual preventive maintenance exists to find the components that are quietly degrading before they produce the event you are currently experiencing. A capacitor declining from its rated microfarad value toward failure produces no symptom that is observable to a homeowner without a capacitor tester. It fails without announcement, at which point the compressor draws locked rotor amperage attempting to start, stresses the compressor, windings, and what was a $40 part replacement on a maintenance visit converts to a $1,500 to $2,800 compressor replacement if the degraded capacitor ran until complete failure. Condenser coil fouling from accumulated debris reduces heat rejection efficiency by 10 to 30% and requires a trained technician with appropriate access to identify and correct. Heat exchanger inspection requires removing furnace panels and examining the exchanger under operating conditions. Refrigerant charge verification requires gauge manifold readings at service ports. None of these tasks are performable by a homeowner without equipment, which is why the service visit exists and why its findings are not visible during normal system operation. The Air Conditioning Contractors of America found that systems receiving annual maintenance fail at approximately 40% lower rates over a 10-year period than unmaintained systems. Most manufacturer extended warranties on new equipment require documented annual maintenance by a licensed technician as a condition of coverage. Skipping service can void a warranty claim on a repair that would otherwise have been covered at no parts cost to you. The 5 years of declined agreements are the direct explanation for this morning's call. The maintenance was not solving problems you could see, it was preventing the one you now have. 42. You purchased a window air conditioner, decided the exhaust hose looked aesthetically unacceptable in the window, and have been operating the unit in the center of the room with the exhaust hose coiled behind it for the past 2 weeks. The room has not cooled. You'd like to return the unit as defective. The unit is not defective. It is currently functioning as a space heater. A portable or window air conditioner removes heat from room air across the evaporator coil, concentrates that heat, and must transfer it somewhere. In a correctly vented configuration, the concentrated heat exits through the exhaust hose to the outdoors. When the hose is coiled behind the unit in the same room, the concentrated heat has nowhere to go except back into the space from which it was just removed. The net thermal effect on the room is positive, meaning the room gets warmer with the unit running than it would without it, because the unit is also consuming electricity, which converts entirely to heat as a byproduct of its operation. You are running an appliance that is adding heat to the space you are trying to cool. The room temperature is climbing because the machine is working exactly as designed, with the output routed back to the input. Every portable AC unit ships with an exhaust hose and window installation hardware, specifically because the hose is not optional equipment. It is the mechanism by which the system functions at all. Single hose portable units also draw conditioned indoor air for condenser cooling and exhaust it outdoors, which must be replaced by warm outdoor air infiltrating through the building envelope. This makes them less efficient than window units even when correctly vented. None of that applies here because the unit has not been correctly vented for 2 weeks. The defect is in the installation, not the product. 43. You noticed a small puddle of clear liquid beneath your outdoor heat pump unit, documented it with photographs, concluded it was compressor oil leaking from a failing compressor, and are ready to proceed with system replacement before the compressor seizes. The puddle under your heat pump is water, and it is there because your heat pump is working correctly. During the defrost cycle, in which the heat pump briefly reverses its refrigerant flow to melt ice accumulation off the outdoor coil, the ice liquefies and drains off the base pan of the unit, producing a visible puddle directly beneath it. This happens regularly during heating season in cold, humid conditions, sometimes multiple times per hour if ambient temperatures and humidity levels are favorable to coil icing. On humid summer operating days, cold refrigerant lines connecting the outdoor unit to the indoor air handler develop condensation on their exterior surfaces, which may drip near the unit. This is the same physical process as condensation on a cold glass and carries the same implications. None. Compressor oil is mixed with refrigerant and circulates through the sealed refrigerant circuit. It does not accumulate in the outdoor base pan under normal conditions. A refrigerant leak significant enough to carry compressor oil out of the system would also produce a detectable sweet chemical odor at the leak point, a measurable pressure drop on gauge readings, and reduced system performance, none of which are present here. The only liquids near an outdoor unit that warrant concern are oily residue with a chemical smell at a specific fitting, rust-colored water indicating corrosion in the drain pan, or glycol from a ground source heat pump loop. Clear water under a heat pump that is running defrost cycles is evidence of a heat pump that is running defrost cycles. The photographs are not needed for this diagnosis. 44. You've researched geothermal heating and cooling, you understand it uses heat from the earth, and you'd like to install a system and eliminate your electricity bill. You've budgeted for the installation cost only. Geothermal heat pump systems are remarkably efficient. They are not free to operate, and the distinction between those two things matters considerably when you're planning a household budget. The ground loop exchanges thermal energy with the earth at depths where ground temperature remains stable at approximately 50 to 60 degrees Fahrenheit year-round in most U.S. locations. This stable thermal reservoir is what the system extracts heat from in winter and rejects heat to in summer. What the system uses electricity to do is run the compressor, the circulator pump moving fluid through the ground loop, and the air handler blower. None of those components operate without purchased electricity. What changes is the efficiency at which that electricity delivers thermal energy. Geothermal systems achieve KOP values of 3 to 5 under most operating conditions, meaning 3 to 5 units of heat for every 1 unit of electricity consumed. A standard air source heat pump delivers 2 to 3.5 units under favorable conditions. Electric resistance heat delivers 1 unit. The efficiency advantage is real and significant, particularly in climates with high heating loads or high summer temperatures where air source systems struggle against outdoor air conditions. Installation costs reflect the ground loop work, $15,000 to $30,000 or more depending on loop type, soil conditions, and system size. The federal tax credit under the Inflation Reduction Act currently covers 30% of installation costs through 2032, which meaningfully adjusts the payback period. Annual maintenance of the mechanical components remains necessary. The earth provides the thermal reservoir for free. The equipment that accesses it runs on electricity you will continue to purchase every month. 45. You know what refrigerant is in your system because the service port caps are blue, and blue means R22, which you've explained to the technician now standing at your outdoor unit. The technician is going to disregard this information entirely and read the nameplate instead. Service port cap colors are not a standardized system for identifying refrigerant type in residential HVAC equipment. They are not assigned by any industry body, are not regulated by any standard, and carry no consistent meaning across manufacturers, installers, or supply houses. The color of a Schrader valve cap reflects what was in the technician's parts bag the last time someone opened those ports. ASHRAE has established color codes for refrigerant supply cylinders used by technicians. R22 cylinders are green, R410A cylinders are rose, R134A cylinders are light blue. Those color codes apply to the cylinders technicians carry, not to the caps installed on your equipment. The authoritative identification of refrigerant type is the unit nameplate, affixed to both the outdoor condenser and indoor air handler, which lists refrigerant type, factory charge, weight, and operating pressure ranges. This is the document that was attached to the equipment at the factory by the manufacturer, and it is the only identification that matters for any service decision. The stakes of misidentification are not trivial. R22 and R410A operate at dramatically different pressures. R410A high side pressure reaches 400 to 600 psi. R22 high side pressure reaches 250 to 300 psi. Adding R410A to an R22 system or any refrigerant to a system containing a different refrigerant produces system pressures and chemical interactions that can exceed component design ratings and cause failure. When the nameplate is missing or unreadable, a refrigerant identifier tool analyzes the circuit contents directly. The cap color contributes nothing to this process. 46. You have one room that is consistently hotter than the rest of the house, and your solution is to add another supply register to that room. You'd like the technician to cut a register opening in the ceiling while they're here for the tune-up. Adding a supply register without adding duct capacity does not create additional airflow. It divides the existing airflow among more outlets. If the branch duct serving that room is already operating at its design capacity, the new register and the existing register will each produce reduced airflow compared to what the single register was delivering, because the total air volume available to that branch has not changed. You have distributed the same amount of air across more holes without improving the room's comfort at all. The hot room problem almost certainly has a different cause. Hot rooms in homes with otherwise adequate conditioning are typically caused by one or more of the following: insufficient insulation in the exterior walls or ceiling of that room, excessive solar gain through south or west-facing windows, an undersized branch duct that was never delivering adequate airflow to begin with, or a return air deficit. A room with supply air and no return air path develops positive pressure that resists additional supply airflow. The solution to a return air deficit is a transfer grill, jump duct, or dedicated return, not another supply register pushing against the same resistance. Manual deduct design assigns specific airflow requirements to each room based on its individual thermal load. If the branch duct to the problem room was undersized at original installation, adding registers downstream of an undersized duct produces no improvement. A dedicated ductless mini-split for the problem room is frequently the most effective and most cost-efficient resolution, providing independent capacity without modifying the existing duct system. More holes at the ceiling do not fix a problem that lives in the branch duct or the wall insulation. 47. Your attic-mounted air handler has a condensate drain line that your previous installer terminated in the attic rather than routing it to an appropriate discharge point. The installer told you the condensation would evaporate up there. Your living room ceiling now has a water stain the size of a dining table, and you'd like to know what happened. A residential air handler in cooling mode produces 1 to 3 gallons of condensate per hour of operation. In a humid summer climate, a system running 8 to 12 hours per day generates 8 to 36 gallons of water per day. Attic insulation, whether fiberglass, bats, or blown cellulose, has no meaningful evaporative capacity when continuously saturated. It becomes a moisture reservoir that maintains the surrounding wood structure at elevated moisture content. Roof decking, typically OSB or plywood, begins to develop mold growth at moisture content above 19%. Structural integrity of load-bearing wood members begins to decline at moisture content above 28%. A condensate line, terminating freely in an insulated attic, achieves these moisture levels within weeks during peak cooling season. The installer's assurance that the condensate would evaporate was arithmetically false. A properly terminated condensate drain exits the building through a wall penetration to a visible outdoor location, into a utility sink or floor drain, or through a condensate pump to an appropriate discharge point. A secondary drain line with visible exterior discharge is required by code in many jurisdictions for attic-mounted systems, specifically to alert the homeowner when the primary drain has clogged. float switches in the secondary drain pan, cut system power before overflow occurs, and cost under $30. The water in your ceiling traveled from the air handler to the drain pan overflow to the attic insulation to the ceiling assembly below it, 1 gallon at a time every day for however long the system ran. It did not evaporate. 48. You have a zoned HVAC system with motorized dampers, and you've closed every zone except your home office because you want the office at 65 degrees while the rest of the house remains unoccupied. The system trips repeatedly and you believe the zone controller is faulty. The zone controller is responding correctly to a static pressure condition you created by closing every zone except one. A zoned HVAC system installs motorized dampers in the duct branches and a zone controller that responds to multiple thermostats, but the equipment at the center of the system, the air handler, the furnace, the compressor, retains the same fixed capacity it had before the zoning equipment was installed. When all zones close except one, the system's rated airflow must pass through a single branch duct that was designed for a fraction of total system airflow. Static pressure spikes, airflow drops. The evaporator coil temperature drops below 32 degrees Fahrenheit. The coil begins to ice. The system short cycles and eventually trips on safety controls. This is not a zone controller fault. It is a fundamental mismatch between total system airflow and available duct capacity. Properly designed zoning systems include a bypass damper, a pressure relief component that opens into a common area when system static pressure exceeds a set threshold, preventing exactly this condition. Systems installed without bypass dampers rely on the installer having configured minimum zone sizes that prevent all zones from closing simultaneously. Your installation has neither. True variable capacity equipment, specifically modulating furnaces and inverter-driven heat pumps, addresses this more gracefully because they can reduce total output to match a single zone load. Single-stage equipment cannot modulate below its minimum firing rate. Achieving 65 degrees in a single room while the rest of the home is physically isolated at a different temperature requires either a separate system for that room or a correctly designed and bypass-equipped zoning installation. What you have is neither. 49. You cannot smell anything wrong with your indoor air, your home is air-conditioned, the filter was changed sometime last year, and you're declining any discussion of air quality products on the basis that if something were wrong with the air, you would be able to detect it. The most significant indoor air pollutants are specifically the ones that exist below or outside the human olfactory detection range. The EPA ranks indoor air pollution among the top 5 environmental health risks, and estimates that indoor air in the average American home can be 2 to 5 times more polluted than outdoor air. Radon, a naturally occurring radioactive gas seeping from soil into basements and crawl spaces, is the second leading cause of lung cancer in the United States at 21,000 deaths annually per the CDC. It is completely odorless. It requires a test kit to detect. Carbon monoxide, as established earlier in this list, is also odorless. Formaldehyde off-gases from pressed wood products, new flooring, and cabinetry at concentrations below the olfactory threshold for many people and is associated with respiratory irritation and long-term cancer risk. Fine particulate matter, smaller than 2.5 microns, produced by cooking, candles, printers, and outdoor infiltration, penetrates deep into lung tissue and is invisible to the naked eye. Pet dander consists of microscopic protein fragments from skin, saliva, and dried urine that remain airborne for hours and accumulate throughout the home, regardless of whether an odor is detectable. ASHRAE standard 62.2 defines minimum mechanical ventilation requirements for residential buildings. Most homes built before 2010 rely on uncontrolled air infiltration that has become increasingly inadequate as building envelopes have been tightened through energy upgrades. Your nose is not calibrated for any of these. The absence of a detectable odor is not air quality data. It is the absence of olfactory data, which is a completely different and significantly less useful thing. 50. Your current furnace is 60,000 BTU, and you'd like it replaced with a 120,000 BTU unit. because last winter was uncomfortable and more capacity will solve the problem. You've decided this before the technician has said a word. This is item 4 applied to heating, and it generates an identical set of problems through an identical mechanism. A furnace rated at twice the required capacity heats the space so rapidly that the thermostat is satisfied before warm air has had time to distribute evenly through the home. The burner fires, the heat exchanger reaches operating temperature, the thermostat measures rising temperature at its location, reaches set point in 3 to 5 minutes, and shuts the system down. Distant rooms, basement spaces, and areas with lower register airflow have received minimal conditioning. The thermostat location is comfortable, everywhere else is not. This is short cycling, and it repeats continuously throughout the heating season. Furnace sizing is determined by manual J load calculation, accounting for home square footage, ceiling height, and insulation values, window area, infiltration rate, and local design heating temperature. Doubling the BTU rating without a load calculation produces the system size for a home twice the thermal load of yours. Short cycling also causes accelerated heat exchanger fatigue. Every time the furnace cycles on and off, the heat exchanger expands from cold to hot and contracts back. A correctly sized furnace cycling 3 to 4 times per hour accumulates far fewer thermal stress cycles than an oversized furnace cycling 8 to 10 times per hour. And heat exchanger cracks develop along fatigue lines created by exactly this kind of repeated thermal shock, years earlier than they would on a correctly sized unit. The correct response to last winter's discomfort is a manual J calculation to find the actual cause, which is almost never insufficient furnace capacity. 51. Your home feels stuffy, the air seems stale, and you've concluded the HVAC system is bringing in too much outdoor air and recirculating it through the house. You'd like the outdoor air intake blocked. Your central forced air HVAC system is recirculating indoor air. It is not actively introducing outdoor air. This is the direction of operation that is making you uncomfortable. A standard residential ducted system pulls air from the living space through the return grills, conditions it in the air handler, and delivers it back to the living space through the supply registers. This is a closed loop. No outdoor air enters the system in standard operation. The stuffiness you're describing is caused by insufficient fresh air exchange, not by excessive outdoor air introduction. Carbon dioxide accumulates from human respiration. Volatile organic compounds accumulate from building materials, cleaning products, and cooking. Humidity from showering and cooking builds without dilution. These accumulate specifically because the system is recirculating the same indoor air continuously, which is the opposite of what you diagnosed. ASHRAE Standard 62.2 defines minimum mechanical ventilation requirements for residential buildings. Most homes built before 2010 have no mechanical ventilation system designed to meet this standard and rely on incidental air infiltration through the building envelope, which has decreased as homes have been better weatherized. The solution is a controlled fresh air introduction mechanism, an energy recovery ventilator or heat recovery ventilator that exchanges measured volumes of indoor and outdoor air while transferring thermal energy to minimize conditioning losses, or a simpler fresh air damper on the return duct that admits outdoor air during system operation. Blocking the outdoor air pathway you don't currently have would make the stuffiness significantly worse. The problem is that you need more outdoor air exchange, not less. The intervention you're requesting is the opposite of the remedy. 52. You went to the auto parts store, purchased several cans of refrigerant with the built-in pressure gauge, added 2 cans to your home air conditioning system, and you're calling because it still isn't cooling, and you'd like to know how many more cans to add. The cans you purchased are formulated for automotive air conditioning systems using R134A or R12134YF. Your home HVAC system uses R410A. These are different refrigerants with different thermodynamic properties, different operating pressures, and different compressor oil compatibility. Adding automotive refrigerant to a home HVAC system introduces an incompatible substance into a refrigerant circuit that was designed, charged, and sealed around a completely different compound. The pressure-temperature relationship of R410A requires a low side operating pressure of approximately 100 to 120 psi under normal cooling conditions. Automotive R134A operates at low side pressures of 25 to 45 psi. The built-in gauge on the consumer cans you purchase is calibrated for automotive pressures. The reading it displayed when you connected it to your home system was meaningless. Consumer refrigerant cans also commonly include stop leak additives, polymer-based compounds designed to seal minor leaks in automotive AC components. When introduced into a residential HVAC system, these additives contaminate the refrigerant, clog the metering device, and foul the compressor oil, typically requiring a complete system flush or compressor replacement to resolve. R410A is not sold in consumer cans at any retail location because EPA Section 608 certification is required to purchase it. The system you've added automotive refrigerant to now contains a contaminated mixture of incompatible compounds. The compressor is working against a refrigerant blend it was not designed for. Adding more cans will not improve the situation. A technician will need to recover the contaminated charge, assess compressor condition, flush the system, repair the original leak, and recharge with the correct refrigerant. The cans made everything more expensive. 53. You've been running every bathroom exhaust fan in the house continuously all summer because moving air around helps cool the home and the fans assist the air conditioning somehow. You'd also like to know whether larger exhaust fans would help further. Exhaust fans remove conditioned air from the home and exhaust it to the outdoors. For every cubic foot per minute of air removed, an equal volume of outdoor air must infiltrate through gaps in the building envelope to replace it because your home cannot sustain a partial vacuum. In summer, that replacement air arrives at whatever outdoor temperature and humidity the environment provides. A standard residential bathroom exhaust fan moves 50 to 110 CFM. Running 3 fans simultaneously removes 150 to 330 CFM of air that your air conditioning system has already cooled and dehumidified. Replacing it with outdoor air, your system must now recool and dehumidify from ambient conditions. Your air conditioning system is working against the exhaust fans continuously. Bathroom exhaust fans serve one specific purpose: removing humidity at the source during and immediately after showering. The correct operating duration is during the shower and 20 to 30 minutes afterward. At that point, the localized humidity spike has been addressed, and continued operation removes conditioned air from the home for no benefit. Kitchen range hoods are significantly more powerful, ranging from 200 to 1200 CFM depending on the model. Running a 600 CFM range hood for 2 hours exhausts the approximate conditioned air volume of a 1500 square foot home. The correct approach to whole home ventilation is a balanced system that introduces and exhausts measured equal volumes of air while transferring thermal energy, not uncontrolled exhaust, through bathroom fans that depressurize the home and drive uncontrolled infiltration through the least sealed gaps in your building envelope. Larger fans would make this worse at a higher cost. 54. Your HVAC system has a compressor failure and a refrigerant leak. The unit is 17 years old, it uses R22, and the technician has recommended replacement. You're certain the technician is fabricating the diagnosis to sell a new system, and you'd like a second opinion that confirms the system is fine. A failed compressor on a 17-year-old R22 system is one of the clearest replacement cases in residential HVAC, and no technician needs to fabricate it. R22 was phased out of production and import in the United States on January 1, 2020 under the Clean Air Act. All R22 currently in circulation is reclaimed, recycled stock from systems already decommissioned. Prices have risen from approximately $5 per pound in 2010 to $50 to $150 per pound or more depending on regional availability. Repairing a failed compressor on the system requires sourcing a compatible R22 compressor at current market pricing, purchasing reclaimed R22 at current market pricing, performing the full repair, and returning a 17-year-old system with other components at or near end of expected service life to operation. The 50% rule suggests that if repair cost approaches 50% of replacement cost for comparable new equipment, replacement is the more economically rational decision. At current R22 pricing and compressor replacement labor costs, the repair frequently exceeds that threshold on its own. A second opinion is entirely appropriate for a major expenditure. A legitimate compressor failure is confirmed by measuring locked rotor amperage, checking for winding ground faults, verifying pressure differentials, and testing contactor function. Ask the second technician to show you those measurements. If they confirm what the first technician found, which they will, you have two independent diagnoses on a 17-year-old R22 system with a dead compressor. The diagnosis is unwelcome. That is not the same thing as fabricated. 55. Your main return air grill is completely blocked by a large sectional sofa that has been against that wall for 3 years, and you cannot identify any changes you made to the house during the period when everything stopped feeling comfortable. The return air system is the intake side of the HVAC circuit. It draws air from the living space back to the air handler to be conditioned and redistributed. Blocking the primary return grill is not a minor restriction. In most homes, the main return grill handles 60 to 80% of total system return airflow. With that grill blocked, the blower motor is attempting to move its rated airflow volume through whatever small gaps and secondary returns remain available, which is not enough. On ECM motors, the motor ramps up to compensate, drawing higher amperage and generating more heat. On older PSC motors, airflow simply drops and the motor runs against elevated static pressure continuously. The evaporator coil receives less warm air, its temperature drops below 32 degrees, ice forms, airflow drops further, and the drain pan fills from the thawing cycle. In heating mode, the heat exchanger retains heat, it cannot transfer to insufficient airflow, the high limit switch trips, and the furnace short cycles. Return air grills are large by design. Moving a specific volume of air through a grill without generating excessive pressure requires a large face area at low velocity. You cannot make the grill smaller or more aesthetically manageable without adding additional return locations to compensate for the reduced opening. Solutions exist. Decorative return covers with the same open area, furniture placement that maintains 6 inches of clearance minimum, or a return air pathway through an adjacent closet. The sofa looks excellent where it is. The HVAC system has been telling you about it for 3 years. You filed the feedback under unexplained comfort issues and left the sofa there. 56. You're nostalgic for R22 and you've expressed to the technician that the newer refrigerants are inferior products pushed by environmental regulation and manufacturer interest, and that R22 simply worked better. You'd like the technician to agree with you before the conversation continues. R22 was phased out because it belongs to the HCFC class of refrigerants, meaning it contains chlorine atoms that, when released into the atmosphere, catalytically destroy stratospheric ozone molecules. A single chlorine atom can destroy thousands of ozone molecules before being deactivated. This is atmospheric chemistry with documented, measurable global consequences. The Montreal Protocol, signed in 1987 by 197 countries, including the United States, established the international framework for phasing out ozone-depleting substances based on scientific evidence of ozone layer depletion and its associated increase in UVB radiation reaching the Earth's surface. This was not a marketing decision. R410A, the primary residential replacement, contains no chlorine and carries zero ozone depletion potential. It carries a high global warming potential, which is why it is now being phased down under the AEM Act of 2020 in favor of refrigerants including R32, R454B, and R290, each with substantially lower climate impact. In terms of thermodynamic performance, R410A operates at higher pressures than R22 and achieves comparable or superior energy efficiency in correctly designed systems. No field performance data supports the conclusion that R22 systems were more efficient than their successors. What you likely remember as superior performance was the performance of a well-maintained system in its prime operating years, which is a condition of maintenance and age rather than refrigerant chemistry. The transition away from R22 was inconvenient and expensive for the industry and for homeowners with existing equipment. It was also correct. The technician is not going to agree with you on this one. 57. Your outdoor unit has been making an intermittent rattling sound for a few months. You've attributed it to leaves or seasonal debris and mentioned it at the end of the service call as an afterthought while the technician is packing up. Intermittent rattling from an outdoor condenser is not a seasonal ambient noise. It is a diagnostic signal with a specific list of probable causes, and 2 of them will take the entire unit down if left unaddressed past a certain point. Condenser fan blade imbalance, caused by a blade bent from debris impact or shifted on its hub, creates vibration that transmits through the motor shaft to the motor bearing. Continued operation with an imbalanced blade accelerates bearing wear at a nonlinear rate. A failing condenser fan motor bearing produces intermittent rattling that progresses to continuous grinding before the bearing seizes, at which point the condenser fan stops, airflow across the condenser coil drops to 0, head pressure spikes, and the compressor shuts down on high pressure protection. Fan motor replacement runs $200 to $500. Compressor replacement runs $1,500 to $2,800. The rattle was the announcement. The seized bearing and the failed compressor are the consequence of treating the announcement as background noise. Loose refrigerant line sets vibrating against the cabinet create a rattle that is initially harmless but can develop into copper tubing fatigue at the contact point over time, eventually producing a refrigerant leak at the wear location. A compressor developing an internal mechanical knock produces a rhythmic metallic sound that tracks with compressor RPM and indicates terminal wear requiring compressor replacement. Debris inside the unit is the most benign cause and is confirmed and resolved by opening the unit and cleaning it, which takes 15 minutes. The technician is still standing next to the unit. This is the moment to investigate the rattle, not the moment to defer it until next season. 58. You purchased a portable air conditioning unit, found the exhaust hose installation visually objectionable, placed the unit in the center of the bedroom with the hose coil behind it, and you're calling because the unit is defective and the room has become noticeably warmer since you turned it on. The unit is not defective. It is heating your room. A portable air conditioner removes heat from room air across its evaporator coil, concentrates that heat at the condenser coil, and must transfer it to an exterior environment through the exhaust hose. With the hose coiled behind the unit in the same room, the concentrated heat has no exterior environment to transfer to. It discharges directly back into the space from which it was removed. The compressor and all other electrical components also convert their consumed electricity entirely to heat as a byproduct of operation. The net thermal effect of running the unit without external venting is a room that accumulates heat from the condenser output and the electrical consumption simultaneously. The room temperature climbs because the machine is adding heat to the space faster than the evaporator side can remove it from the immediate air in front of the unit. This is not a malfunction. It is the predictable result of routing the output back to the input. Every portable AC unit ships with a window installation kit because the hose is not an accessory. It is the component that makes the machine a cooling device rather than a heating device. Single hose portable units also draw indoor conditioned air for condenser cooling and exhaust it outside even when correctly vented, creating a makeup air infiltration problem that reduces efficiency compared to window units. None of those efficiency considerations apply to your current situation because the unit has not been correctly vented at any point since you purchased it. Return the unit if you like. The defect will not be found in the product. 59. Your furnace was inspected last year and the heat exchanger was clear. You're declining this year's inspection on the basis that heat exchangers don't develop problems in a single heating season and the prior clearance covers the current year. Heat exchangers fail through thermal fatigue. Repeated heating and cooling cycles expand and contract the metal along stress lines that propagate over time, and the rate at which those stress cycles accumulate depends entirely on how the furnace has been operating since the last inspection. A furnace short cycling due to a dirty filter, a blocked return, or an oversized installation accumulates thermal stress cycles at a rate several times higher than a correctly operating unit. A furnace that cycled 8 to 10 times per hour for an entire heating season because the filter wasn't changed experienced dramatically more fatigue than one that cycled 3 to 4 times per hour under correct conditions. Last year's inspection certifies last year's condition under last year's operating pattern. It does not certify the current season. Cracks in heat exchangers frequently do not present during visual inspection of a cold unit at rest. They open under differential thermal expansion when the exchanger reaches operating temperature and may close again when cooled, making cold inspection an incomplete diagnostic method. Combustion analyzer testing, which compares CO levels in the flue gas against CO in the supply airstream simultaneously during operation, is the method that catches breaches that are invisible at rest. A rising supply air CO reading when the blower activates during analyzer testing indicates combustion gas contamination of the conditioned airstream, with the crack producing no visible indication on a cold inspection. Heat exchanger warranties from many manufacturers run 20 years or for the life of the equipment, meaning a covered crack on a newer furnace is a zero parts cost replacement. Declining the inspection does not reduce the probability of a crack existing. It reduces the probability of finding it before it matters. 60. You've been turning the air conditioning completely off on the hottest days of summer to protect the equipment from overheating and extend its lifespan, and you've been doing this for several years under the impression that it constitutes responsible equipment stewardship. The equipment does not need your protection from hot weather. It was designed, tested, and rated for operation at outdoor ambient temperatures, reaching 115 degrees Fahrenheit in most manufacturers' specifications. A 95-degree summer afternoon is well within its operational envelope. What you're doing on the hottest days of the year is removing conditioning from the home during the period of highest thermal load, allowing the building's thermal mass to absorb the maximum available heat energy during peak solar hours, and then restarting the system in the early evening against an 85 to 90 degree indoor temperature with a fully heat-saturated building structure. This is the most demanding operating condition you can impose on the system. The full pull-down from a heat-saturated structure at elevated indoor temperature during peak ambient conditions is harder on the compressor than steady-state operation at a maintained set point, because the startup event draws the highest electrical load in the compressor's operating cycle, and the extended pull-down keeps the system running at full output for hours rather than modulating toward a maintained condition. Compressor lubrication is maintained by refrigerant circulation during operation. A compressor that is off is not circulating oil. Frequent full off to full on cycles across large temperature differentials produce more wear events per cooling season than continuous steady operation. Additionally, peak utility pricing and time of use rate markets runs from the mid-afternoon through the evening, which is exactly the window when you restart the system at its most energy-intensive operating point. The equipment was built for the hottest day of the year. Protecting it by turning it off on that specific day is protecting it from the thing it exists to do. 61. Someone told you at some point that running the air conditioning below 72 degrees will cause the system to freeze up, and you've maintained 72 as a hard lower limit for several years, tolerating discomfort rather than risk damaging the equipment. The system will not freeze because of a low thermostat set point. Evaporator coil freezing occurs when the coil temperature drops below 32 degrees Fahrenheit due to insufficient airflow across it or insufficient refrigerant pressure within it. Those conditions are produced by a clogged filter, a blocked return, closed vents, or low refrigerant charge, not by the temperature you select on the thermostat. A correctly maintained system with clean coils, an appropriate filter, correct refrigerant charge, and unrestricted return airflow will operate without freezing at any reasonable residential set point. The evaporator coil chills refrigerant to approximately 40 degrees regardless of whether the thermostat calls for 68 or 72. The coil temperature is determined by refrigerant pressure and airflow conditions, not by the differential between room temperature and set point. If a previous technician observed freeze up at low set points and advised you to stay above 72 degrees, the freeze up was caused by one of the airflow or refrigerant conditions listed above. The instruction to avoid low set points was a workaround for an unresolved underlying problem, not a fundamental operational limit of your equipment. Set points below 68 degrees are unusual for comfort reasons in residential applications, but they are mechanically permissible on a healthy system. Cold storage applications, server rooms, and medical facilities regularly operate ducted systems at 60 degrees and below without icing events. The constraint was placed on you to work around something that should have been diagnosed and repaired. The limit was never in the equipment, it was in the condition of the equipment at that time. 62, your mini split has a DRI mode setting and you've been running it exclusively in DRI mode all summer because you read that it uses less electricity than cool mode. The house isn't reaching a comfortable temperature on the hottest days, and you're calling to ask whether you need a larger unit. You need to switch to cool mode. Dry mode on a mini split operates the compressor at reduced capacity and cycles it more frequently than cool mode, prioritizing moisture removal over temperature reduction. The fan runs at a lower speed to maximize contact time between room air and the cold coil, which improves dehumidification efficiency but dramatically reduces total heat removal capacity. On a day where the outdoor temperature is in the upper 80s or 90s, the thermal load exceeds what a reduced capacity operating mode can manage. The room temperature rises above set point while the humidity remains controlled, which is the condition you've been describing as the unit not keeping up. Dry mode is the correct operating mode for mild, humid days where the outdoor temperature is in the mid-60s to low 70s, and the discomfort is caused primarily by elevated relative humidity rather than by heat. On those days, dry mode can maintain comfort with less total energy consumption than cool mode because less total heat removal is required. On a hot summer afternoon, that context does not apply. Energy consumption in DRI mode is not dramatically lower than cool mode in absolute terms because the compressor still runs. The savings are relative to running cool mode when only dehumidification was needed. Running DRI mode when full cooling capacity is required produces higher indoor temperatures, longer compressor runtime trying to compensate, and the same or greater electricity consumption compared to running cool mode and reaching set point efficiently. The unit is the correct size. The operating mode was the issue. 63, you have a functioning heat pump and you've supplemented it with several plug-in electric space heaters placed around the home because you believe the combination is cheaper than running the heat pump for the full house. Your electricity bill has climbed substantially and you cannot identify why. The space heaters are the bill. Electric resistant space heaters operate at 100% efficiency, 1 unit of electricity in, 1 unit of heat energy out. Your heat pump in heating mode operates at 150 to 300% efficiency depending on outdoor temperature, delivering 1.5 to 3 units of heat for every unit of electricity consumed because it is moving thermal energy from outdoor air rather than generating heat from electrical resistance. A standard 1500 watt space heater produces approximately 5,118 BTU per hour. A heat pump delivering the same 5,118 BTU per hour at a COP of 2 consumes 750 watts. The space heater costs exactly twice as much per BTU delivered at that COP. At a COP of 3, the space heater costs 3 times as much. Running multiple space heaters simultaneously to reduce heat pump runtime does not lower your heating costs. It replaces the most efficient heating source in the home with the least efficient form of electric heat available and compounds it by running several simultaneously. 4 1500 watt space heaters running at the same time draw 6 kilowatts continuously. Beyond cost, the NFPA identifies space heaters as the leading cause of home heating fires, responsible for approximately 1,700 residential fires annually with 80 associated deaths. If the heat pump is underperforming and creating the perceived need for supplemental space heaters, the correct response is to diagnose and repair the heat pump. The space heaters are not a supplemental strategy, they are a more expensive and more dangerous replacement for a system that should be fixed. 64. You read an article about smart home security vulnerabilities, unplugged your smart thermostat, reverted to a manual thermostat, and you'd like confirmation that your home network is now secure. The smart thermostat was not the meaningful vulnerability in your home network, and removing it has not meaningfully changed your security exposure. Smart thermostats from major manufacturers collect occupancy data via motion sensors, temperature readings, and schedule preferences, which are transmitted to manufacturer cloud servers for remote access and optimization features. This is not financial data, identity data, or communications data. The documented cybersecurity vulnerabilities in smart thermostats have primarily involved network pivoting, which is using the thermostat as an entry point to reach other connected devices on the same network. This threat is mitigated by placing IoT devices on a separate guest network isolated from your primary devices, which costs nothing and takes approximately 10 minutes to configure on most modern routers. The most commonly cited smart thermostat security demonstration was a proof of concept performed by researchers in a controlled environment at a security conference, not a documented attack on residential thermostats in the field. Your home network currently contains devices with meaningfully greater data exposure than a thermostat. Smartphones with camera and microphone access, smart televisions that frequently include cameras and active listening features, computers, and a router whose administrative password may still be the factory default. Removing the thermostat while leaving all of those devices unchanged and on the same flat network is a selective security measure that addresses the lowest risk device in the home. The energy savings from a properly functioning smart thermostat are estimated by the EPA at 10 to 15% of annual heating and cooling costs. You have traded a documented financial benefit for a security improvement that is, at best, marginal relative to the other attack surfaces currently operating in your home. Put the sensors back on a guest network. 65. You have central air conditioning and you're confused about why there's mold in the corner of the master bedroom and a persistent musty smell in the basement because the AC handles humidity and the house is air conditioned. Central air conditioning removes moisture from indoor air as a byproduct of the cooling process, but it is not a dehumidifier, and the conditions under which it provides adequate humidity control are more limited than most homeowners realize. The system removes humidity only while it is running in active cooling mode. During spring and fall, when outdoor temperatures are mild and the cooling load is low, the system may run for short periods or not at all, and humidity accumulation in the home continues without active removal. Basements present a specific and largely independent humidity problem. They are cooler than above-grade spaces, receive less supply airflow in most residential duct designs, and are in direct contact with soil moisture through the foundation walls and floor slab. Basement humidity is substantially driven by ground moisture and is not effectively managed by a system primarily designed to condition the floors above. ASHRAE identifies the mold growth threshold at sustained indoor relative humidity above 60%, a condition commonly found in basements and crawl spaces even in homes with functioning central air conditioning during humid seasons. A standalone or whole home dehumidifier removes moisture independently of the cooling cycle on a humidity set point, allowing control during mild weather and in spaces the AC system does not adequately serve. Whole home units integrate with the existing duct system and operate autonomously from the thermostat. The EPA's guidance on mold prevention recommends maintaining indoor relative humidity below 60%. Central air conditioning alone frequently cannot meet that target during shoulder seasons or in below-grade spaces. The AC is doing what it was designed to do. Humidity control in those specific conditions requires a dedicated tool. 66. You'd like more airflow in the home, and you've concluded that installing a larger blower motor will push more air through the duct system. You'd like the technician to source the upgrade. Blower motor size and airflow in a duct system are not directly proportional in the way you're imagining. Airflow in a forced air system is governed by the static pressure curve of the duct system, which is the relationship between airflow volume and the resistance the duct network presents to that flow. A given duct system has a fixed resistance for a given airflow rate. Adding motor power does not change the duct's resistance. If the duct system is the constraint, more motor produces more static pressure against the same restriction, draws more electricity, generates more heat in the motor, increases velocity noise at the registers, and may actually deliver the same or marginally less net airflow if the increased resistance drives the motor into an inefficient operating region. ECM motors, which are standard in most current residential equipment, are already programmed to ramp their output to deliver a target airflow in cubic feet per minute, regardless of static pressure fluctuations within their operating range. They self-optimize for the duct system they are installed in up to their maximum output. Replacing one with a larger ECM motor provides meaningful additional airflow only if the existing motor was operating at its absolute output limit, which is not the typical residential condition. The correct approach to increasing system airflow is reducing duct system resistance, enlarging undersized branch ducts, eliminating unnecessary elbows, correcting kinked or compressed flex duct runs, and adding return air capacity where it is deficient. These changes lower the resistance the existing motor works against, allowing it to deliver more airflow within its current output range. The obstacle is not the motor, it is the pipe the motor is pushing through. Upgrading the motor without addressing the pipe produces a more expensive version of the same result. 67, you have a 2-story home and you've relocated the thermostat to the upper floor because heat rises and you want the system to manage the upstairs temperature accurately. The downstairs is now significantly overcooled in summer and the system runs constantly. In a single-zone forced air system, the thermostat controls the entire system. When the thermostat is satisfied, all conditioning stops for every space the system serves. The location of the thermostat determines which space's comfort is prioritized, and all other spaces receive conditioning only as long as the thermostat location continues calling for it. Heat does rise, which means the upper floor of a 2-story home is naturally warmer in summer due to solar gain through the roof assembly and thermal stratification. An upper floor thermostat reaches its cooling set point sooner than a main floor thermostat would under the same conditions, shutting the system off before the main floor has received adequate conditioning. The main floor, where occupants typically spend the majority of waking hours, is underserved. The system cycles on and off more frequently because the upper floor satisfies and recovers faster than the full building load dictates. The correct solution for a 2-story comfort problem is a 2-zone system with separate thermostats on each floor, each controlling its own motorized damper zone and serving the floor it measures. This is an engineering solution. Moving the thermostat to the upper floor is a comfort optimization for the floor you sleep on at the expense of the floor you live on, executed without additional engineering. Smart thermostats with remote sensors allow temperature averaging across multiple locations, effectively managing a weighted average of upstairs and downstairs conditions from a single device and thermostat location. This is a software solution to the same problem at considerably lower cost than a full zoning installation. The thermostat placement determines whose comfort is prioritized. The upstairs is now in charge. 68. Every summer when the air conditioning comes on for the first time, someone in the household gets sick and you've concluded the AC is spreading germs. You'd like it serviced before anyone else catches whatever the AC is distributing. Air conditioning does not cause colds. Colds are caused by rhinovirus and a collection of more than 200 other respiratory viruses that require transmission from an infected person or a contaminated surface. No study has established a causal relationship between air conditioning operation and increased rhinovirus transmission. The temporal correlation you've observed, illness coinciding with AC startup, is attributable to the other things that happen simultaneously in late spring and early summer: increased social activity, end of school year gatherings, and the introduction of whatever viruses have been circulating in the environments your household members have recently occupied. What the AC system can do, if poorly maintained, is circulate dust, accumulated allergens, and mold spores from a dirty coil or contaminated duct system, producing respiratory irritation, allergy symptoms, and general malaise that feel clinically identical to a mild cold but are not viral infections. A dirty evaporator coil colonized with the biofilm from item 18, a duct system that has accumulated years of particulate matter, and a filter that has not been changed adequately all contribute to a first-run air quality event when the system starts for the season after months of dormancy. The correct preventive measure is system maintenance before the season begins, professional coil cleaning, duct inspection, filter replacement, and drain line treatment. This addresses the actual indoor air quality event that correlates with seasonal startup. It does not, however, address the rhinovirus that someone brought home from the graduation party last weekend, which is the illness you will get regardless of how recently the coil was cleaned. Maintain the system, wash your hands. The viruses have no relationship with your thermostat settings. 69. You're adding a sunroom to your home and you'd like to extend the existing HVAC ductwork into the addition yourself. You have tin snips, sheet metal screws, and a clear sense of how duct systems work. You'd like to know the appropriate duct size to use. A sunroom addition represents one of the highest per square foot cooling loads of any residential space you can build. South and west facing glass maximizes solar gain, the lightweight structure has minimal thermal mass to buffer temperature swings, and the glazing area relative to floor area is typically much higher than in a conventional room. The additional load may require 1 to 3 tons of equivalent cooling capacity, depending on the size and orientation of the addition. Extending a branch duct from an existing system does not add cooling capacity, it redistributes existing capacity. Adding a new branch to an existing trunk increases the total airflow demand on the system. If the existing equipment was already operating at or near its rated output serving the original home, the new branch reduces airflow and conditioning to every existing zone by pulling pressure from the shared trunk. The existing rooms become underserved while the new addition receives inadequate airflow from a branch duct that was sized for a fraction of the system's total output. A dedicated ductless mini-split for the sunroom is the standard industry recommendation for this scenario. Independent capacity matched to the high load of the addition, no impact on the existing system, and independent temperature control suited to a space with highly variable solar gain throughout the day. Building permits for additions in most jurisdictions require HVAC plans from a licensed contractor. DIY ductwork without permits creates code violations that complicate insurance claims and resale. Sheet metal screw connections without mastic sealant leak conditioned air into the wall cavity immediately. The tin snips are the right tool for a different job. 70. You've noticed a sharp burning smell that you would describe as electrical coming from the air handler. You've opened several windows to clear the smell, and you're calling to schedule a service appointment for Thursday. The system is still running. A sharp electrical burning odor from an air handler is a potential electrical fire in progress. It is not a scheduling item. Something inside a device that is actively moving high-velocity air through every room in your home is overheating, and that air is now carrying the byproducts of that overheating into every space the duct system reaches. The system needs to be turned off now, not on Thursday. The correct sequence is to go to the thermostat and set it to off, then locate the disconnect switch near the air handler, typically a red-handled switch on the wall, and turn that off as well. An electrical burning smell from HVAC equipment can indicate a blower motor, winding failure, generating heat from insulation breakdown, a control board component failure, a capacitor venting electrolytic fluid under thermal stress, arching at a loose wire connection under load, or a foreign object in contact with a motor. Air handlers are typically located in attics, mechanical closets, or utility rooms, adjacent to combustible materials including wood framing, insulation bats, and stored items. A smoldering electrical component in these locations has a direct path to a structural fire. If the smell is strong or accompanied by visible smoke, call 911 from outside the mechanical space before re-entering. The distinction between this and the first startup dust smell from item 21 is specific. Seasonal dust. Burn-off smells musty and dusty and dissipates in 30 minutes. Electrical component failure smells sharp, chemical, and plastic adjacent, and does not dissipate as long as the source remains energized. The appointment on Thursday assumes the building is still standing on Thursday. Shut it off now. 71. Your electricity bill doubled compared to the same month last year. The HVAC system is your first suspect, and you'd like to schedule a replacement before the next billing cycle. You started working from home 8 months ago and got a dog 6 months ago. Before replacing a system that may be functioning correctly, work through every variable that changed in the home before the bill increased. Working from home adds approximately 10 to 15% to residential energy consumption on average, according to the American Council for an Energy Efficient Economy, from computers, monitors, lighting, and small appliances running 8 to 10 additional hours per day. A dog generates between 250 and 350 BTU per hour of body heat continuously, adds to the household's sensible cooling load, and typically results in the owner leaving the air conditioning running at a lower set point when the animal is home alone. The comparison should be made in kilowatt hours consumed rather than dollars paid, because utility rate increases of 10 to 30% occur annually for most customers and inflate the dollar amount without any change in consumption. HVAC systems do lose efficiency gradually as components age, but a decline sufficient to double consumption in a single year requires a specific diagnosable failure, a failed compressor running continuously at locked rotor amperage, a refrigerant charged so low the system cannot cycle off, or a failed reversing valve in a heat pump locking it in one mode. All of these produce additional symptoms beyond a high bill. Review your utility's online usage history in kilowatt hours by month, compare to the previous year month by month controlling for weather, and identify when the increase began relative to when your life changed. The bill doubled because something changed. The question is whether it was the equipment or whether it was you. Most of the time, it's you. Check the data before you replace the system. If you want to see more, click the video on screen now.